Teaching a computer to see is one of the greatest challenges in software engineering. Humans recognize a face, a car, or a street sign in fractions of a second without consciously thinking about visual structure. For artificial intelligence, processing a single photo historically caused massive bottlenecks, overloading system memory and slowing performance to a crawl. Solving this breakdown required a fundamental shift in design: the convolutional neural network. Instead of trying to analyze an entire photo all at once, a convolutional network scans small local patches step by step, recognizing basic lines, forming complex patterns, and building full visual intelligence. Consider what an image actually is to a computer. To a human, an image is a scene filled with objects, light, shadows, textures, and depth. To a computer, an image is nothing more than a structured multidimensional array of numbers, which software engineers refer to as a tensor. If we look at a standard digital photograph, it is structured as a three-dimensional grid defined by height, width, and depth. The height and width represent the spatial dimensions, measured in pixels. A single pixel is the smallest individual element of a digital image. The third dimension, depth, corresponds to color channels. In a standard digital image format, we have 3 color channels: red, green, and blue. Each pixel at a specific coordinate contains 3 separate numbers ranging from 0 to 255, representing the intensity of red, green, and blue light at that exact physical point. A value of 0 represents total darkness or complete absence of light, while 255 represents maximum intensity. If an image has a resolution of 1000 pixels in width and 1000 pixels in height, it contains 1 million individual spatial locations. Because each location has 3 color channels, the entire image consists of 3 million distinct numbers. Imagine attempting to process this 3 million number array using a traditional fully connected neural network, also known as a multilayer perceptron. In a fully connected network, every single input value must connect to every single artificial neuron in the first hidden layer. If your input layer has 3 million values, and your first hidden layer contains just 1000 artificial neurons, every single hidden neuron requires 3 million distinct weights. A weight is a learnable numerical parameter that determines how strongly a particular input signal influences the output of a neuron. Multiplying 3 million inputs by 1000 neurons means that a single hidden layer would require 3 billion parameters. If you add a second hidden layer of equal size, you add billions more parameters. This parameter explosion creates catastrophic engineering challenges. First, storing billions of floating point numbers consumes enormous amounts of graphics memory and system memory. Second, calculating the mathematical updates for billions of weights during training requires tremendous computational power, leading to unacceptably slow training cycles. Third, and most importantly, a fully connected network suffers from severe overfitting when exposed to billions of parameters. Overfitting occurs when a machine learning model memorizes the exact pixel values of the training data instead of learning generalizable patterns, causing it to fail completely when presented with new, unseen images. Beyond the parameter explosion, fully connected networks suffer from a fundamental architectural flaw when applied to visual data. They destroy spatial relationships. In a fully connected network, the multidimensional image array must be flattened into a single one-dimensional vector of numbers before being fed into the model. When you flatten a two-dimensional grid of pixels into a one-dimensional line, Pixels that were originally adjacent to each other vertically are suddenly separated by thousands of elements in the vector. A human face, a car wheel, or a tree branch consists of continuous groups of neighboring pixels that share local visual context. By flattening the grid, the network loses all structural awareness of top, bottom, left, right, and diagonal spatial relationships. Furthermore, fully connected networks lack translation invariance. Translation invariance means that an object should be recognized regardless of where it appears in the frame. If a fully connected network learns to recognize a cat in the top left corner of an image, moving that cat to the bottom right corner changes every single input value entering the network. The model has to relearn what a cat looks like at every possible spatial coordinate, making it extraordinarily inefficient and brittle. To overcome these fundamental limitations, computer vision architects designed the convolution operation. The core philosophy of a convolution is to process visual data locally rather than globally, preserving spatial grid structures while drastically reducing parameter count. Instead of connecting every single neuron to every input pixel across the entire image at once, a convolutional layer applies a small, localized window of weights that slides across the spatial dimensions of the input array. This small window of weights is known as a filter or a kernel. Visualize a kernel as a small physical stencil or magnifying glass held over a large grid of numbers. Typical kernels are square grids with dimensions such as 3 pixels by 3 pixels or 5 pixels by 5 pixels. Unlike the massive inputs of a fully connected layer, a 3 by 3 kernel contains only 9 individual weight values. When applied to an image, the kernel starts at the top left corner. It overlays its 9 weights on top of the 9 corresponding input pixels directly beneath it. The network then performs an element-wise multiplication. The first weight is multiplied by the first pixel value, the second weight by the second pixel, and so on for all 9 positions. Once all 9 multiplications are complete, the network sums the 9 resulting numbers together into a single scalar value. A scalar is simply a single numerical quantity. This process of element-wise multiplication followed by summation is known mathematically as a dot product. After computing the dot product for the top left region, the kernel steps to the right by a specified distance, overlays its weights on the next localized group of pixels, computes a new dot product, and records another single number. The kernel continues this sliding motion from left to right across the row. When it reaches the rightmost edge of the image, it moves down by a specified step size and begins scanning the next row from left to right. This systematic scanning process across the entire spatial height and width of the input array is what we call convolution. The output produced by sliding this kernel across the input grid is a brand new two-dimensional array of numbers, known as a feature map or an activation map. Every number inside a feature map represents how strongly the input pixels in a specific localized region matched the patterns encoded within the kernel's weights. If the numbers in a kernel are mathematically arranged to detect horizontal edges, the kernel will produce a high output value whenever it slides over a sharp horizontal transition between light and dark pixels. When it slides over a smooth, uniform region like a clear blue sky, the multiplications cancel out, producing an output value close to 0. Thus, the feature map acts as a spatial heat map, highlighting exactly where specific visual characteristics exist within the original image. To fully grasp how convolutions operate on real-world color images, we must extend our mental model from 2 dimensions to 3 dimensions. A color image is not a single 2-dimensional grid. It is a 3-dimensional volume with a depth of 3 color channels. red, green, and blue. Therefore, a convolutional kernel must also be a three-dimensional volume. If we choose a spatial kernel size of 3 pixels by 3 pixels, the kernel's actual structural dimension must be 3 by 3 by 3. The spatial dimensions are 3 by 3, and its depth automatically matches the channel depth of the input volume, which is 3. When this three-dimensional kernel overlays a region of the color image, it covers a 3 by 3 spatial grid across all 3 color channels simultaneously. It performs 27 individual element-wise multiplications, 9 for the red channel, 9 for the green channel, and 9 for the blue channel. All 27 results are summed together into a single scalar number. As the three-dimensional kernel slides across the height and width of the image volume, it generates a single two-dimensional feature map layer. In practice, a single convolutional layer does not use just one kernel. It uses a bank of multiple distinct kernels running in parallel. If a convolutional layer contains 64 separate 3 by 3 by 3 kernels, each individual kernel is initialized with different random weights. During training, each kernel learns to look for a completely different visual pattern. One kernel might learn to detect vertical edges, another might look for diagonal color gradients, another for circular shapes, and another for high-contrast corner points. Because each of the 64 kernels generates its own two-dimensional feature map, stacking all 64 feature maps together creates a brand new three-dimensional output tensor. The height and width of this output tensor correspond to the spatial dimensions resulting from the sliding scan, while the depth of the tensor is exactly 64, corresponding to the number of kernels used in that layer. This brings us to one of the most powerful concepts in convolutional networks: parameter sharing. In a fully connected network, every input connection had its own unique weight. In a convolutional layer, the same kernel weights are reused across every single spatial location as the filter slides across the image. The 9 weights inside a horizontal edge detection kernel are applied at the top left corner, the middle, the bottom right, and everywhere else across the frame. This design makes 2 profound engineering guarantees. First, it enforces translation equivariance. Translation equivariance means that if a visual pattern shifts its location in the input image, the activation in the feature map shifts by the exact same distance, allowing the network to detect features regardless of their spatial coordinates. Second, it drastically reduces the number of trainable parameters. Instead of needing billions of weights, a convolutional layer with 64 3 by 3 kernels operating on 3 color channels requires only 64 multiplied by 27 weights, which equals less than 2,000 parameters. By replacing billions of unconstrained weights with a small set of spatially shared kernels, convolutional layers eliminate parameter explosion while preserving local geometric structure. To precisely control the spatial output size of a feature map and manage computational complexity, software engineers tune 2 critical hyperparameters during convolutional layer design: stride and padding. A hyperparameter is a configuration setting chosen by the engineer before training begins, rather than a weight learned automatically by the model. The first hyperparameter, stride, defines the step size of the sliding kernel. A stride of 1 means the filter advances by exactly 1 pixel at a time as it moves horizontally and vertically across the grid. Every neighboring position is evaluated, resulting in a dense, high-resolution output feature map. However, if we increase the stride to 2, the kernel moves 2 pixels forward with every step, skipping every other spatial location. Moving with a stride of 2 reduces both the spatial height and the spatial width of the resulting feature map by roughly half. which cuts the total number of output values by 3/4. Increasing stride is a computationally efficient way to downsample the spatial dimensions of an image tensor, reducing memory footprint and processing requirements in deeper layers. However, setting the stride too large carries a risk. If the step size is larger than the kernel width, the filter skips over regions of the image entirely, potentially missing small, high-frequency visual details. The second hyperparameter, padding, addresses a problem that occurs at the boundaries of the image grid. When a kernel slides across an unpadded image, the pixels along the outermost perimeter are covered far fewer times than the pixels located near the center. A pixel in the exact middle of an image is included in multiple overlapping dot product steps as the kernel moves across surrounding neighborhoods. In contrast, a pixel in the extreme top left corner is only touched once, when the kernel is positioned at its starting location. Furthermore, because a kernel requires a full local neighborhood to compute a dot product, it cannot center itself directly over a perimeter pixel without extending beyond the boundary of the image. As a result, every time a convolution is applied without boundary adjustments, the output feature map shrinks spatially. A 3x3 kernel applied to a 10x10 image yields an 8x8 feature map. If you stack 10 consecutive convolutional layers without padding, the spatial dimensions shrink continuously until the feature map disappears entirely. To prevent boundary shrinkage and ensure edge pixels are given equal weight, engineers apply zero padding. Zero padding involves adding a border of artificial pixels containing the numerical value 0 around the outer edges of the input grid before running the convolution. In computer vision terminology, we categorize padding into two primary configurations: valid padding and same padding. Valid padding means applying 0 additional pixels around the border. Under valid padding, the kernel is restricted strictly to valid internal coordinates, allowing the spatial dimensions to shrink naturally with each layer. Same padding means calculating and adding precisely enough zero-padded borders around the input so that the output feature map maintains the exact same spatial height and width as the input array when using a stride of 1. For a 3x3 kernel, adding a 1-pixel border of zeros around all 4 sides allows the kernel to center itself directly on the original corner pixels. The outer elements of the kernel overlay the zero-padded border, computing a valid dot product without shrinking the dimensional grid. Using same padding allows deep convolutional architectures to stack dozens or hundreds of layers without losing spatial resolution prematurely, keeping the coordinate space aligned across complex multi-layer networks. Simply sliding linear kernels across pixel arrays and computing dot products is not enough to solve real-world visual tasks. A dot product is a purely linear mathematical operation. A linear operation is one where the output is directly proportional to the input, obeying the mathematical properties of additivity and scaling. If you stack 10 consecutive linear convolutional layers without any nonlinear intervention, the entire chain of layers mathematically collapses into a single equivalent linear operation. No matter how many millions of linear layers you assemble, a linear system can only learn simple linear decision boundaries. Real-world visual data is overwhelmingly nonlinear, filled with complex curves, occlusions, changing illumination, and intricate structural hierarchies. To enable convolutional networks to learn complex nonlinear representations, every convolutional layer must pass its output feature map through an activation function. An activation function is a mathematical function applied element-wise to every number in a tensor, introducing nonlinearity into the network's calculations. The most widely used activation function in modern convolutional neural networks is the rectified linear unit, abbreviated as ReLU. The mathematical rule governing ReLU is remarkably simple. For any input value, if the number is greater than 0, ReLU leaves it unchanged. If the number is 0 or negative, ReLU converts it directly to 0. Despite its simplicity, ReLU introduces crucial properties that transform network training. By clamping all negative values to 0, ReLU introduces sparsity into the feature maps. Sparsity means that a portion of the neurons remains silent or inactive for any given input, allowing the network to activate distinct pathways for different visual stimuli. Additionally, ReLU solves a major historical training issue known as the vanishing gradient problem. Prior to the adoption of ReLU, neural networks primarily used saturating activation functions like the sigmoid or hyperbolic tangent functions. Sigmoid functions squeeze all input values into a narrow range between 0 and 1. When input values become very large or very small, the slope of the sigmoid function flattens out to near 0. During backpropagation, the algorithm used to calculate mathematical updates for model weights using gradients. Multiplying by these near-zero slopes causes the gradient signal to shrink exponentially as it flows backward through deep layers. By the time the signal reaches the earliest layers, the gradients vanish completely, leaving early weights unable to update or learn. ReLU avoids saturation for all positive inputs because its slope for any positive number is exactly 1. This constant slope creates an unobstructed mathematical corridor for gradient signals to flow backward, allowing networks to grow dozens of layers deep without learning stalling out. However, standard ReLU has a known failure mode called the dying ReLU problem. If a large gradient update forces a neuron's weights into a state where it outputs negative values for every single training image, that neuron will output 0 continuously. Because the slope of ReLU is 0 for all negative numbers, backpropagation can never route a non-zero gradient back through that neuron again. The neuron becomes permanently inactive, effectively dying and wasting computational capacity. To mitigate the dying ReLU issue, researchers created variants such as the leaky rectified linear unit, or leaky ReLU, and the Gaussian error linear unit, known as GELU. Leaky ReLU modifies the negative region of the function. Instead of converting negative values strictly to 0, it multiplies negative inputs by a small scalar constant, such as 0.01. This creates a slight downward slope for negative numbers, ensuring that even inactive neurons maintain a small, non-zero gradient flow, allowing them to recover during optimization if needed. GELU takes a smoother probabilistic approach, scaling inputs by their probability under a Gaussian distribution. This creates a smooth, continuous curve that slightly dips below 0 before ascending, providing superior optimization dynamics in modern advanced vision architectures. Beyond ReLU, leaky ReLU, and GELU, modern computer vision backbones leverage advanced mathematical nonlinearities designed to maintain self-normalizing properties and dynamic gating, exponential linear units, scaled exponential linear units, and swish functions. Exponential linear units, abbreviated as ELU, address the dying ReLU problem by replacing 0 output for negative inputs with a smooth exponential curve defined as alpha multiplied by the quantity of e raised to the power of x minus 1. Because ELU outputs small negative values for negative inputs, the mean activation of the feature map is pushed closer to 0. Bringing mean activations close to 0 produces a natural self-normalizing effect similar to batch normalization, speeding up gradient learning while maintaining robustness against negative saturation. Scaled exponential linear units, known as SELU, take self-normalization to a rigorous mathematical limit. SELU multiplies the ELU function by a precise fixed scaling constant lambda, approximately equal to 1.0507, and sets alpha to approximately 1.6732. Under strict mathematical proofs, passing activations through SELU layers with proper weight initialization guarantees that the mean and variance of activations across deep layers automatically converge towards zero mean and unit variance without needing explicit batch normalization layers. The swish activation function, also known as the sigmoidal linear unit or CLU, defines activation as x multiplied by the sigmoid function of beta multiplied by x, where beta is either a constant or a learnable parameter. Swish exhibits a unique non-monotonic curve. For positive values, it behaves similarly to ReLU, but for small negative values, it dips smoothly below zero before ascending back towards zero. This smooth, non-monotonic shape creates a continuous loss landscape, preventing gradient clipping and improving optimization stability in modern mobile backbones like EfficientNet. As visual data flows forward through consecutive convolutional layers combined with nonlinear activation functions, a fundamental property emerges: the expansion of the receptive field. Understanding the receptive field is critical for mastering computer vision architecture. The receptive field of an individual neuron in a feature map refers to the total spatial area of the original input image that can directly influence that neuron's value. In the very first convolutional layer of a network, a neuron in a feature map generated by a 3x3 kernel has a receptive field of exactly 3 pixels by 3 pixels. It can only see and react to local pixel variations within that immediate 9-pixel square. It is completely blind to the rest of the image. Now, consider what happens when we stack a second convolutional layer on top of the first feature map, also using a 3x3 kernel. A single neuron in the second layer looks at a 3x3 neighborhood of neurons in the first feature map. But each of those first-layer neurons was already looking at a 3x3 patch of the original input image. Because neighboring first-layer neurons overlap in their view of the original input, the single second-layer neuron effectively receives information from a 5-pixel by 5-pixel region of the original input image. Its receptive field has expanded from 3x3 to 5x5. If we add a third 3x3 convolutional layer, the receptive field of a neuron in that third layer expands to 7 pixels by 7 pixels of the original image. As we stack deeper and deeper layers, especially when combined with downsampling operations like stride or pooling, the spatial receptive field of neurons grows exponentially. Early layers in a convolutional network have tiny, localized receptive fields, allowing them to detect low-level, high-frequency visual primitives such as individual edges, sharp corners, color transitions, and fine textures. Middle layers have moderate receptive fields, allowing them to combine edge activations into mid-level visual structures like curves, parallel lines, textures, and simple geometric shapes. Deepest layers have massive receptive fields that cover nearly the entire input image, allowing them to synthesize mid-level shapes into high-level semantic concepts, such as recognizing an entire human face, a dog's ear, a car wheel, or a building facade. This progression from localized low-level primitives to global semantic abstractions forms the core foundation of hierarchical visual representation in artificial intelligence. To fully comprehend how convolutional neural networks learn during backpropagation, we must unpack the exact mathematical calculus of backpropagation through a convolutional layer. In a standard fully connected layer, computing the gradient of the loss function with respect to weights is a straightforward vector matrix multiplication. In a convolutional layer, because kernel weights are spatially shared across every position of the input grid, the calculus requires understanding how gradients accumulate across spatial sliding windows. When a convolutional layer passes an input tensor forward to produce an output feature map, each individual weight in a kernel contributes to multiple dot product operations across the entire spatial grid. Consequently, during backpropagation, the total gradient of the scalar loss function with respect to a single kernel weight is equal to the sum of all local gradients computed at every spatial position where that weight was applied. Mathematically, the gradient of the loss function with respect to the kernel weights is computed by performing a two-dimensional cross-correlation between the original input tensor and the incoming gradient tensor backpropagated from the subsequent layer. Simultaneously, to pass the gradient signal backward to the preceding layer, the network must compute the gradient of the loss function with respect to the input tensor. This calculation is executed by performing a full two-dimensional convolution between the incoming gradient tensor and a spatially flipped version of the kernel weights, rotated by 180 degrees. Spatially flipping the kernel weights ensures that the chain rule of calculus correctly tracks which input pixels influenced which output feature map activations. This elegant mathematical duality, where forward propagation applies convolution with the original kernel, and backward propagation applies convolution with the flipped kernel, enables fast, vectorizable gradient computation on modern parallel graphics hardware. While convolutional layers are exceptionally skilled at extracting spatial features across local neighborhoods, stacking convolutions alone creates a massive data storage challenge. As an image passes through dozens of convolutional layers with hundreds of parallel kernels, the network generates huge stacks of high-resolution feature maps. Processing and storing these full-resolution feature tensors throughout deep networks demands unsustainable memory bandwidth and computing power. Furthermore, fine-grained pixel coordinates are often overly sensitive to tiny, irrelevant fluctuations in input images. If a camera shifts by a single pixel, the raw pixel array changes, but the high-level semantic content remains identical. To reduce computational complexity, control memory usage, and build spatial robustness, convolutional neural network architectures rely on pooling layers. A pooling layer is a specialized downsampling operation designed to reduce the spatial height and width of feature maps while preserving their channel depth and dominant visual information. Unlike convolutional layers, standard pooling layers contain zero learnable parameters or weights. They do not learn during backpropagation. Instead, a pooling layer applies a fixed, deterministic mathematical rule across localized spatial regions of an input feature map. To visualize how pooling operates, imagine a two-dimensional feature map resulting from a convolutional layer. A pooling window, typically defined as a square grid of 2 pixels by 2 pixels, slides across the feature map with a stride of 2. Because the window size is 2 by 2 and the step size is 2, the pooling window moves across non-overlapping patches of the grid, touching every input value exactly once. As the window sits over a 2 by 2 block of 4 numbers, it evaluates those 4 values using its specified mathematical rule, outputs a single summary number, and then steps 2 pixels to the right. The two most fundamental types of pooling are max pooling and average pooling. Max pooling operates by selecting the single largest numerical value within the localized pooling window and discarding the remaining 3 values. If a 2 by 2 grid contains the numbers 1, 3, 8, and 2, max pooling outputs 8. The intuition behind max pooling is directly tied to how feature maps represent visual patterns. Remember that high positive numbers in a feature map indicate the strong presence of a specific visual feature, such as a sharp vertical edge or a bright corner point. Lower numbers or zeros indicate that the feature is absent. By retaining only the maximum value within each local region, max pooling preserves the strongest visual activation present in that neighborhood while discarding lower, background activations. Max pooling provides a crucial architectural benefit known as local translation invariance. Because max pooling selects the peak activation within a window, small spatial shifts of the feature within that local patch do not change the output value. If a sharp edge moves slightly to the left or right due to camera shake or minor object movement, as long as its peak activation remains within the bounds of the 2x2 pooling window, the maximum value extracted by max pooling remains identical. This allows the network to become robust against minor spatial translations, distortion, and position variance in the input data. Furthermore, applying a 2x2 max pooling layer with a stride of 2 achieves a 75% reduction in the total number of spatial values in the tensor. The height is halved, and the width is halved. Because 4 spatial values are compressed into 1, the computational burden on all subsequent layers is reduced by 3/4. Importantly, max pooling performs this spatial reduction independently across every channel in the input volume. If the input tensor has a depth of 64 feature maps, max pooling processes all 64 channels separately, producing an output tensor with the exact same channel depth of 64, but with half the spatial height and half the spatial width. Average pooling, by contrast, operates by calculating the arithmetic mean of all 4 values within the pooling window. If a 2x2 grid contains the numbers 1, 3, 8, and 2, average pooling adds them together to get 14, divides by 4, and outputs 3.5. Rather than focusing exclusively on the single strongest peak activation, average pooling summarizes the overall background intensity and general presence of features across the local patch. The trade-off between max pooling and average pooling reflects a fundamental choice in architectural behavior. Max pooling tends to preserve sharp, high-contrast features, crisp edges, and prominent visual landmarks, making it the historical default choice for early convolutional networks focused on object classification and detection. Average pooling produces a smoother, softer downsampling effect, blending local features together. While average pooling can sometimes wash out sharp, low-level edge responses in early layers, it shines in specific contexts where smooth spatial aggregation is preferred over extreme peak extraction. A powerful evolution of average pooling is global average pooling. Global average pooling takes spatial reduction to its absolute extreme limit. Instead of sliding a small 2x2 window across local patches, global average pooling evaluates an entire feature map across its entire spatial height and width at once. If an intermediate layer produces an array of 64 feature maps, where each map has a spatial dimension of 7 pixels by 7 pixels, global average pooling computes the average of all 49 numbers within each separate 7 by 7 grid. The output of global average pooling is a one-dimensional vector containing exactly 64 numbers, one single average scalar value for each feature map channel. This operation completely collapses the spatial dimensions of height and width down to 1 by 1, retaining only the channel dimension. Global average pooling plays a transformative structural role in modern convolutional neural networks, particularly as a replacement for traditional fully connected classification heads. In early network architectures, the final multidimensional feature map volume was flattened into a massive vector and fed into several dense, fully connected layers to perform classification. Those dense, fully connected layers accounted for up to 80% of the model's total trainable parameters, making the network prone to severe overfitting and demanding immense memory bandwidth. By placing a global average pooling layer directly at the end of the convolutional feature extractor, architects can compress each high-level feature map into a single scalar value representing the overall presence of a complex semantic concept across the entire image. This one-dimensional summary vector can be fed directly into a small final classification layer without needing massive, fully connected intermediate matrices. This structural shift offers three profound engineering advantages. First, it eliminates millions of weights, drastically reducing model size, preventing overfitting, and accelerating inference speed. Second, because global average pooling computes spatial averages regardless of resolution, it allows a trained convolutional network to accept images of varying spatial heights and widths at inference time without breaking network dimensions. Third, it enforces a direct, interpretable correspondence between individual feature maps and target categories. Each feature map can be interpreted as a global detector for a specific class or object part, creating cleaner feature representations. However, downsampling feature maps through pooling or strided convolutions involves an inherent architectural trade-off: spatial information loss. Every time spatial dimensions are halved, detailed positional coordinates are permanently discarded. In tasks like image classification, where the model only needs to answer what object is present in the frame, discarding fine positional coordinates is acceptable and often beneficial, as it yields translation invariance. But in tasks like object detection, medical image segmentation, or autonomous driving, where the network must determine exact pixel-level spatial boundaries and pinpoint precise location coordinates, losing spatial resolution creates severe errors. To overcome spatial rigidity and enhance spatial adaptability without losing resolution, modern architectures incorporate spatial transformer networks and deformable convolutions. A fundamental challenge in classic convolutional architectures is that convolutional filters are fixed in shape and spatial orientation. If an input image contains an object that is rotated by 45 degrees, scaled down to a small corner, or distorted by perspective skew, the network must rely on data augmentation and deeper layers to learn invariant representations. Spatial transformer networks, universally known as STNs, solve this by introducing an explicit, differentiable spatial transformation module that can be inserted into any stage of a convolutional network. An STN consists of three specialized components: a localization network, a grid generator, and a sampler. The localization network is a mini-convolutional model that receives an intermediate feature map and outputs a vector of continuous spatial transformation parameters, denoted as theta. For a 2D affine transformation, theta consists of 6 floating point numbers encoding translation offsets, rotation angles, scaling factors, and shearing parameters. The grid generator takes these predicted theta parameters and constructs a sampling grid across the input feature map, calculating where each output pixel should sample its value from in the input grid. The sampler takes the sampling grid coordinates and extracts input feature values using bilinear sampling. Bilinear sampling computes a weighted average of the 4 nearest neighboring pixels around each fractional coordinate, maintaining an end-to-end differentiable mathematical pipeline. During backpropagation, loss gradients flow through the sampler and grid generator back into the localization network, allowing the STN to learn how to automatically rotate, scale, translate, and crop regions of interest within feature maps. If an input image contains a tilted license plate, the STN learns to predict theta parameters that straighten and normalize the license plate before passing it to downstream classification layers. Similarly, to enable convolutional networks to handle non-rigid objects natively, architectures employ deformable convolutions. In a standard convolutional layer, the spatial sampling grid of a kernel is fixed and rigid, a rigid 3x3 square centered over a specific pixel. A rigid grid assumes that visual features always align cleanly with horizontal and vertical axes. But real-world objects, such as a running animal, a flowing garment, or a curving road, possess arbitrary non-rigid shapes that do not conform to rigid square boxes. Deformable convolutions solve this spatial rigidity by learning dynamic 2D offset vectors for each kernel sampling point. In a deformable convolutional layer, a parallel convolutional branch evaluates the input feature map and predicts a set of continuous floating point offset coordinates, delta x and delta y, for every sampling point in the kernel grid. When the main deformable kernel slides across the feature map, its sampling points are shifted by these dynamic offset vectors, allowing the kernel to warp its receptive field shape dynamically around the exact contours of non-rigid objects. If the network encounters a curving object, the deformable kernel stretches its sampling points along the curve. If it encounters a small condensed object, the kernel contracts its sampling points. Because predicted offset coordinates are continuous floating point values, feature values at shifted locations are calculated using bilinear interpolation, maintaining an end-to-end differentiable pipeline trainable via standard backpropagation. Deformable convolutions dramatically improve object detection and segmentation accuracy for complex, non-rigid targets. To fully appreciate the design of modern vision systems, we must trace the structural evolution of classic convolutional neural network architectures. Long before deep learning became the dominant paradigm across software engineering, computer vision relied on handcrafted mathematical feature descriptors. Engineers manually designed equations to detect edges, corners, and color histograms using algorithms like the scale-invariant feature transform and histograms of oriented gradients. These hand-engineered systems were limited by human intuition. If an engineer did not explicitly write a formula to account for a specific lighting variation, shadow, or camera angle, the system failed. The fundamental breakthrough of convolutional networks was replacing hand-engineered algorithms with data-driven representation learning, where the model automatically learns optimal visual filters directly from training data through backpropagation. An early pioneer in this architectural evolution was the LeNet model, designed specifically for processing small grayscale images of handwritten digits. LeNet established the foundational pipeline pattern that would define computer vision architectures for decades, alternating layers of convolutions and spatial downsampling, followed by dense fully connected layers at the end of the network. LeNet utilized small 5x5 convolutional kernels operating on single-channel grayscale inputs, followed by average pooling layers to compress spatial resolution. Because computational resources were severely constrained when LeNet was designed, the network used sigmoidal activation functions and contained only a few thousand trainable parameters. While effective for simple 10-class digit recognition on low-resolution grids, sigmoidal saturation and limited network depth prevented LeNet from scaling to complex, real-world color imagery. The true paradigm shift in deep computer vision occurred with the emergence of the AlexNet architecture, which demonstrated the immense power of scaling network capacity, training on graphics processing units, and utilizing nonlinear activation functions. AlexNet expanded network depth and parameter count dramatically, featuring 8 trainable layers and over 60 million parameters. To process high-resolution color images containing 3 color channels, the first convolutional layer of AlexNet employed massive 11 by 11 spatial kernels applied with a stride of 4. Using an 11 by 11 filter with a stride of 4 allowed the network to aggressively downsample the raw input spatial dimensions right at the input stage, reducing the initial memory footprint while capturing broad, high-contrast visual primitives across large pixel regions. The second layer used 5 by 5 kernels, while subsequent layers transitioned to stacked 3 by 3 convolutions. Beyond spatial scale, AlexNet introduced 3 critical architectural innovations that became mandatory standards across modern deep learning. First, it replaced saturating sigmoidal functions with the rectified linear unit activation function, accelerating gradient convergence by orders of magnitude. Second, it introduced overlapping max pooling layers. Instead of sliding a 2 by 2 pooling window with a stride of 2, AlexNet used a 3 by 3 pooling window with a stride of 2. Because the step size was smaller than the window width, neighboring pooling regions overlapped, which reduced spatial dimensionality while mitigating the severe spatial information loss typical of non-overlapping downsampling. Third, to combat severe overfitting across its 60 million parameters, AlexNet introduced dropout regularization within its dense, fully connected layers. Dropout is a stochastic regularization technique applied during network training. During each forward pass, dropout randomly deactivates a specified percentage of neurons, typically 50%, by setting their output values to 0. On every training step, a different random subset of neurons is muted. This forces the remaining active neurons to learn robust, independent features rather than relying on co-adaptations with specific neighboring neurons. During inference, dropout is turned off and all neurons are activated simultaneously, scaling their outputs by the dropout probability. This creates an ensemble effect inside a single model, dramatically improving generalization on unseen test data. Despite its success, AlexNet suffered from significant architectural inefficiencies. Its initial large 11 by 11 and 5 by 5 kernels were computationally expensive and parameter heavy. Furthermore, its design was somewhat ad hoc, combining different filter sizes and strides without a unifying structural principle. This inefficiency led to the design of the VGG architecture, designed by the Visual Geometry Group. VGG established a revolutionary principle in deep network architecture, replacing large convolutional filters with stacks of small 3 by 3 filters. VGG proved that arbitrary large kernels, such as 5 by 5 or 7 by 7 filters, are mathematically suboptimal compared to deeply stacked 3 by 3 filters. To understand why stacked 3 by 3 filters are vastly superior, let us compare their receptive fields, parameter counts, and nonlinear expressive power. Consider a single 7 by 7 convolutional layer operating on a tensor with input depth C and output depth C. The 7 by 7 filter covers a 7 by 7 spatial patch of the input in a single step. The total number of parameters in this single layer is 7 multiplied by 7 multiplied by C squared, which equals 49 C squared parameters. Now, consider replacing that single 7 by 7 layer with a stack of 3 consecutive 3 by 3 convolutional layers. As we established in our analysis of receptive fields, a single 3 by 3 layer has a 3 by 3 field of view. The second 3 by 3 layer looks at the first layer, expanding its field of view to 5 by 5. The third 3x3 layer looks at the second layer, expanding its effective receptive field to 7x7. Thus, 3 stacked 3x3 layers cover the exact same 7x7 spatial region of the original input image as a single 7x7 filter. However, let us calculate the parameter count of the 3 stacked 3x3 layers. Each 3x3 layer contains 3 multiplied by 3 multiplied by c squared, which equals 9c squared parameters. Stacking 3 such layers yields 3 times 9c squared, which equals 27c squared parameters. Comparing 27c squared to 49c squared reveals a parameter reduction of over 44%. By replacing one large 7x7 kernel with 3 stacked 3x3 kernels, we achieve the exact same spatial receptive field while using almost half the parameters and computational operations. Furthermore, because each of the 3x3 layers is followed by a nonlinear activation function like ReLU, the 3-layer stack contains 3 nonlinear decisions instead of just one. This dramatically increases the network's mathematical capacity to learn complex, nonlinear feature boundaries without increasing parameter count. VGG formalized this philosophy into a uniform modular design. All convolutional layers use 3x3 kernels with same padding, and all spatial downsampling is performed by 2x2 max pooling layers with a stride of 2. By standardizing module design, VGG allowed networks to grow significantly deeper, scaling to 16 and 19 trainable layers. However, VGG revealed a massive new engineering bottleneck: memory footprint and parameter concentration in dense layers. The final convolutional stage of VGG produced a high-depth feature map volume of 7 by 7 by 512. Flattening this volume into a vector produced 25,848 elements. Connecting this vector to VGG's first dense, fully connected layer of 4,096 neurons required over 100 million parameters in that single matrix alone. Over 80% of VGG's total parameters were concentrated in its final dense layers, creating immense memory bandwidth consumption during training and deployment. To further enhance spatial feature reuse and eliminate parameter redundancy, architectural design evolved beyond sequential stacking to introduce dense convolutional networks, universally known as DenseNet. While classic networks pass features sequentially from layer to layer, DenseNet takes feature reuse to its maximum structural limit by using direct channel concatenation. In a DenseNet block, every single layer receives the feature maps of all preceding layers as its input, and passes its own output feature maps forward to all subsequent layers. If a dense block contains 5 sequential convolutional layers, Layer 1 passes its feature maps to Layer 2, 3, 4, and 5. Layer 2 receives feature maps from Layer 1, computes its output, and passes the concatenated features of both Layer 1 and Layer 2 to Layers 3, 4, and 5. This dense connectivity pattern provides 4 major architectural advantages. First, it eliminates the vanishing gradient problem completely. Every layer has direct, unattenuated access to loss gradients flowing back from the final classification head. Second, it enforces maximum feature reuse. Deep layers can directly access low-level edge primitives from Layer 1 alongside mid-level shape features from intermediate layers. Third, because features are concatenated rather than summed, DenseNet layers can use extremely narrow channel depths, such as generating only 12 or 32 new feature maps per layer, known as the growth rate, drastically reducing the total number of learned parameters compared to standard deep architectures. However, DenseNet introduces a specific hardware memory trade-off: high GPU memory bandwidth consumption. Because every layer concatenates all preceding feature maps along the channel dimension, memory footprint grows quadratically with block depth, requiring specialized memory clearing hooks during training. As deep learning researchers attempted to build networks far deeper than VGG or DenseNet, scaling from 19 layers to 50, 100, or more, they encountered a surprising mathematical wall known as the degradation problem. Common intuition suggested that adding more layers to a neural network should always improve or at least maintain performance. After all, if additional layers are unneeded, the optimization algorithm could theoretically learn identity mappings for those extra layers, leaving performance unchanged. However, empirical experiments revealed the exact opposite. As networks grew deeper beyond a certain threshold, their training accuracy began to saturate and then degrade rapidly. Crucially, the degradation problem was not caused by overfitting. In overfitting, a model achieves near-zero training error but high test error. In the degradation problem, the deeper network exhibited higher training error than its shallower counterpart. The deeper model was failing to optimize even on the training data it was actively learning from. The underlying cause of degradation was twofold: vanishing gradient signals during backpropagation and severe optimization difficulties in deep nonlinear parameter landscapes. When a gradient signal is backpropagated through dozens of unconstrained nonlinear layers, repeated matrix multiplications continuously alter the scale of the gradient. The gradient either explodes to infinity or vanishes to zero, preventing early layers from receiving actionable parameter update signals. To solve the degradation problem and unlock extraordinarily deep networks, architectural design was revolutionized by the invention of the residual network, universally known as ResNet. ResNet solved optimization degradation by introducing residual learning and identity skip connections. In a standard feed-forward convolutional network, each layer or block is tasked with directly learning an underlying target mapping, which we can denote as h of x, where x is the input vector entering the block. Learning an unconstrained, complex transformation h of x from scratch through multiple nonlinear layers becomes exponentially difficult as network depth increases. ResNet reframes this mathematical objective. Instead of forcing the stacked layers to learn the target mapping h of x directly, ResNet reformulates the block to learn a residual mapping, denoted as f of x, defined as h of x minus x. The original target mapping h of x then becomes f of x plus x. To implement this mathematically in hardware, ResNet adds an identity shortcut connection, also called a skip connection, that bypasses the convolutional layers within a residual block. The input vector x is routed around the convolutional block along a parallel path and added directly element-wise to the output of the convolutional block f of x. Visualize a residual block as a two-lane highway. The main lane passes through 2 or 3 consecutive convolutional layers, which apply sliding matrix multiplications, normalization, and ReLU activations to compute f of x. The parallel lane is a clear, unobstructed identity highway that carries the original input tensor x forward untouched. At the end of the block, the tensors from both lanes are summed together element-wise before passing through a final ReLU activation. This simple addition of an identity shortcut connection completely transforms optimization dynamics during backpropagation. When calculating gradients during backpropagation, the mathematical rule for the derivative of a sum states that the gradient of f of x plus x is equal to the derivative of f of x plus 1. The constant value of 1 represents the unobstructed gradient flow passing through the identity shortcut connection. Because of this constant factor of 1, the gradient signal from deep layers can flow directly backward through the identity shortcuts across hundreds of layers without being repeatedly multiplied by small weight matrices. The skip connection acts as a gradient superhighway, guaranteeing that early layers receive a clean, unattenuated gradient signal regardless of how deep the network is built. If the convolutional layers in a particular block are unnecessary, the network can easily push the weights of f of x towards 0, allowing the block to collapse into a pure identity mapping where output equals input. This identity fallback ensures that a deeper network will never perform worse than a shallower network. To optimize computational efficiency in very deep ResNet architectures, such as ResNet 50, ResNet 101, and ResNet 152, architects introduced the bottleneck residual block. In a standard residual block, 2 consecutive 3x3 convolutional layers maintain a constant channel depth. In a bottleneck block, the input tensor passes through 3 consecutive layers designed specifically to compress and restore channel dimensions: a 1x1 convolution, a 3x3 convolution, and a second 1x1 convolution. A 1x1 convolution is a unique mathematical operation where the spatial kernel size is exactly 1 pixel by 1 pixel. Because its spatial size is 1x1, it performs no spatial filtering across height and width. Instead, a 1x1 convolution acts exclusively across the channel dimension. It computes a linear combination of all incoming channels at each individual spatial coordinate. In a bottleneck residual block, the first 1x1 convolutional layer reduces the channel depth of the incoming tensor, for example, compressing 256 channels down to 64. This dimensionality reduction is why it is called a bottleneck. The second layer, a 3x3 convolution, performs spatial filtering on the compressed 64-channel tensor, requiring far fewer floating point operations than operating on 256 channels. The third layer, another 1x1 convolution, restores the channel depth back to 256, allowing the output to be added element-wise to the original input tensor passing along the shortcut connection. Bottleneck designs dramatically reduce computational flops while allowing networks to scale to hundreds of layers. While ResNet focused on deep linear stacking with shortcut connections, another major architectural family explored multi-scale parallel processing within single blocks: the Inception architecture family. The Inception architecture was designed around a fundamental visual dilemma. What is the ideal kernel size for extracting features from an image? In any given photograph, salient visual information appears at vastly different spatial scales. A small object, like a bird sitting on a branch, requires small localized kernels like 3x3 to capture fine details. A large object, like a skyscraper or a commercial airplane spanning the entire frame, requires large spatial receptive fields like 5x5 or 7x7 to capture global structure. Choosing a single fixed kernel size for an entire network forces an unfavorable engineering compromise. The Inception module resolves this dilemma by refusing to choose a single kernel size. Instead, an Inception block applies multiple different convolutional kernel sizes in parallel on the exact same input tensor. Within a single Inception module, the incoming feature map is routed simultaneously into 4 parallel branches: a 1x1 convolution branch, a 3x3 convolution branch, a 5x5 convolution branch, and a 3x3 max pooling branch. Each branch extracts visual patterns at its own distinct spatial scale. The outputs from all 4 parallel branches are then concatenated together along the channel dimension, creating a rich multi-scale feature volume. To prevent the computational cost of parallel branches from exploding, inception modules heavily utilize 1x1 bottleneck convolutions prior to running the larger 3x3 and 5x5 spatial filters. The 1x1 convolutions compress the input channel depth, allowing parallel spatial convolutions to run on low-dimensional representations before channel concatenation. Inception demonstrated that networks can achieve high representational efficiency by expanding laterally in width as well as vertically in depth. To overcome the static weight limitation of standard convolutions, modern vision architectures also incorporate dynamic convolutions, represented by conconv and dynamic conv. In a standard convolutional layer, the filter weights are static once training is complete. The exact same weight matrix is applied to every single input sample regardless of image content. Dynamic convolutions replace static weight matrices with input condition dynamic weights. In a dynamic convolutional layer, a small routing network evaluates the input feature map, calculating a vector of dynamic scalar attention weights that sum to 1 using softmax activation. These dynamic scalar weights are used to compute a weighted linear combination of k different parallel kernel weight matrices stored within the layer. Because the final kernel weights are dynamically synthesized on the fly for each specific input sample, dynamic convolutions increase model representational capacity by orders of magnitude with minimal computational overhead. High-capacity visual samples trigger specialized kernel combinations, allowing the network to adapt its filter responses dynamically to complex visual inputs. As artificial intelligence moves toward deployment on mobile phones, embedded Internet of Things devices, and edge hardware, standard convolutional architectures encountered strict memory, latency, and power constraints. High-end server GPUs can execute trillions of floating-point operations per second, but mobile processors operate under tight thermal budgets and battery limits. Running heavy VGG or ResNet models on edge devices caused high latency, excessive heat, and rapid battery drain. To address the demands of mobile and embedded deployment, researchers invented MobileNet, introducing depthwise separable convolutions. Depthwise separable convolutions factorize standard convolution into two completely separate, lightweight operations: depthwise convolution and pointwise convolution. To understand this factorization, recall how standard 3D convolution works. A standard 3x3 convolutional filter operates on spatial dimensions and channel dimensions simultaneously. If an input tensor has a depth of m channels and the layer generates n output channels, a standard 3x3 filter has dimensions of 3x3 by m. Applying n such filters requires computing spatial dot products across all m channels at once, entailing significant computational complexity. Depthwise separable convolution breaks this coupled operation into two isolated steps. Step 1 is the depthwise convolution. In depthwise convolution, spatial filtering is performed completely independently on each input channel. If the input tensor has m channels, we create exactly m separate two-dimensional 3x3 kernels. The first kernel slides exclusively across the first input channel, the second kernel slides exclusively across the second input channel, and so on. No cross-channel mixing occurs. The output of depthwise convolution is a feature map tensor with the exact same depth m as the input. Step 2 is the pointwise convolution. Pointwise convolution handles cross-channel feature combination. It applies n 1x1 convolutional kernels across the m-channel output of the depthwise stage. As the 1x1 kernels slide across the spatial grid, they compute linear combinations of all m channels at each pixel location, generating n brand new output channels. The computational savings achieved by depthwise separable convolution are extraordinary. Mathematically, the ratio of computational cost between depthwise separable convolution and standard convolution is approximately 1 divided by the number of output channels, plus 1 divided by the spatial kernel size squared. For a standard 3x3 filter, 1 divided by 9 is approximately 0.11. This means depthwise separable convolutions achieve an 8 to 9-fold reduction in computational floating point operations and parameter footprint with only a negligible loss in accuracy, enabling real-time computer vision inference on low-power mobile microprocessors. Regardless of whether a model utilizes ResNet skip connections, inception parallel branches, or MobileNet depthwise separable blocks, training a deep convolutional network from scratch requires huge quantities of labeled data and immense computational infrastructure. If an engineer attempts to train a high-capacity vision network on a small, domain-specific dataset, such as 500 specialized medical X-ray scans, the network will rapidly overfit, memorizing the small training set while completely failing to generalize to new patients. To solve data scarcity and make deep vision models accessible across industries, software engineering relies on transfer learning and fine-tuning. Transfer learning is an architectural workflow where a network trained on a massive general-purpose dataset, containing millions of diverse images across thousands of categories, is repurposed as a foundational starting point for a completely different downstream task. The fundamental justification for transfer learning lies in the hierarchical nature of feature representations inside deep convolutional networks. As we established early layers in a CNN learn universal visual primitives, sharp horizontal and vertical edges, color gradients, Gabor-like directional filters, and basic corner textures. These low-level primitives are domain agnostic. A sharp edge in a high-resolution photograph of a commercial automobile is mathematically identical to a sharp edge in a radiographic lung X-ray or a satellite map. Middle layers learn reusable visual motifs, such as curves, intersecting lines, grid patterns, and elemental shapes. Only the deepest final layers learn specialized semantic concepts specific to the original training categories, such as distinguishing specific dog breeds or vehicle models. Because early and middle layers capture domain-agnostic visual primitives, their learned weights represent a highly optimized general visual feature extractor. Transfer learning leverages this spatial hierarchy through two main deployment strategies: feature extraction and full fine-tuning. In the feature extraction strategy, the engineer takes a pre-trained network backbone and completely freezes all of its convolutional layers. Freezing a layer means locking its weight parameters so that they remain constant and receive zero parameter updates during backpropagation. The engineer then removes the original pre-trained classification head, the final dense layer responsible for the original 1,000 category outputs, and replaces it with a brand new, randomly initialized classification head tailored to the specific target domain, such as a binary classifier for medical pathology. During training on the new target dataset, forward passes compute feature activations through the frozen pre-trained backbone, and backpropagation calculates loss gradients exclusively for the parameters inside the new classification head. Because millions of backbone parameters are frozen, training is blisteringly fast and requires minimal compute. More importantly, because the feature extractor is locked, the model cannot overfit to a small target dataset, leveraging the rich visual primitives learned from millions of general images. In the fine-tuning strategy, instead of leaving all backbone layers permanently frozen, the engineer selectively unfreezes a portion of the convolutional layers, typically the deepest blocks, allowing their weights to be updated gradually alongside the new classification head during backpropagation. Fine-tuning is especially powerful when the target visual domain differs significantly from the original pre-training dataset. For example, satellite imagery captured from low Earth orbit or specialized thermal infrared imaging has structural characteristics that differ from standard ground-level RGB consumer photographs. Unfreezing late convolutional blocks allows the network to adapt its mid-level and high-level feature detectors to the unique spatial statistics of the target domain while preserving universal edge and texture primitives in early layers. To execute fine-tuning successfully without destroying pre-trained knowledge, engineers must manage two critical technical factors: differential learning rates and catastrophic forgetting. A learning rate is a scalar hyperparameter that controls the step size taken by optimization algorithms during parameter updates. If the learning rate is set too large during fine-tuning, the optimization step will jump aggressively across the parameter landscape, completely overriding the delicate, highly optimized pre-trained weights with random gradient noise. This destructive phenomenon is known as catastrophic forgetting, where the network violently discards its pre-trained visual representations, causing validation accuracy to collapse. To prevent catastrophic forgetting, fine-tuning utilizes differential learning rates, also known as discriminative layer-wise learning rates. Under differential learning rates, different layers of the network are assigned exponentially scaled learning rates based on their depth. The new, randomly initialized classification head is assigned the highest learning rate, for example 1,000th, allowing it to learn rapidly from scratch. The deepest unfrozen convolutional blocks are assigned a significantly smaller learning rate, such as 100th of the head's rate, allowing them to adjust gently to target domain nuances. Intermediate layers, if unfrozen, receive even smaller learning rates, while the earliest backbone layers remain frozen with a learning rate of 0. Additionally, engineers often employ progressive unfreezing. Progressive unfreezing begins by training only the new classification head while keeping the entire backbone locked. Once the head has converged to a stable loss minimum, the engineer unfreezes the final convolutional block and trains the combined system with differential learning rates. Staged optimization prevents noisy gradients from an untrained classification head from flowing backward and corrupting the foundational backbone feature extractor. Even when engineers deploy sophisticated convolutional architectures and state-of-the-art transfer learning workflows, machine learning models remain fundamentally constrained by the quality, diversity, and volume of their training data. If a neural network is trained exclusively on crisp, high-resolution photographs taken under bright daylight, it will struggle severely when deployed in real-world environments characterized by heavy shadows, rainy weather, camera motion blur, or unusual viewing angles. In software engineering, this vulnerability is driven by dataset shift and overfitting to spurious visual correlations. To force convolutional networks to learn robust, invariant feature representations, computer vision pipelines rely heavily on data augmentation. Data augmentation is a suite of techniques that artificially expands the size and visual diversity of a training dataset by applying randomized, truth-preserving transformations to input images before feeding them into the network. A truth-preserving transformation is one that alters the raw pixel values of an image without changing its underlying semantic label. For example, if you take a photograph of a commercial truck and flip it horizontally from left to right, the image remains unmistakably a commercial truck. However, at the pixel level, every single number in the spatial matrix has been moved to a new coordinate, presenting the network with a brand new visual sample. By exposing the network to millions of augmented variants during training, we explicitly encode inductive biases into the model. An inductive bias is a set of architectural or data-driven assumptions built into a machine learning system that guides how it generalizes to unseen data. Through data augmentation, we teach the network to become invariant to irrelevant visual fluctuations, such as spatial shifts, minor rotations, lighting changes, sensor noise, and partial occlusions. We categorize data augmentation techniques into 4 primary engineering families: spatial transformations, photometric transformations, occlusion-based regularizations, and multi-image mix-up strategies. The first family, spatial or geometric transformations, alters the structural coordinate space of the input image matrix. Random cropping and resizing is one of the most fundamental spatial augmentations. During each training iteration, the pipeline extracts a random rectangular crop from the original image, spanning, for example, between 60% and 100% of the total area, and then resizes that crop back to the network's standard input resolution using bilinear interpolation. Random cropping forces the network to recognize objects when they are partially framed or zoomed in, preventing the model from relying on specific fixed spatial coordinates or background context. Horizontal flipping mirrors the image grid across its vertical axis. This simple operation doubles the effective dataset size for categories that exhibit natural horizontal symmetry, such as vehicles, animals, and consumer products. However, engineers must exercise caution. Vertical flipping, which mirrors an image top to bottom, is appropriate for satellite imagery or microscopic histology slides where direction is arbitrary, but completely invalid for standard natural images, where flipping an image upside down creates physically unrealistic visual samples. Random rotation rotates the image grid around its center point by a random angle within a specified range, such as -15 degrees to +15 degrees. Rotation forces kernels to learn omnidirectional edge and contour detectors. Affine transformations combine translation, rotation, scaling, and shearing within a single unified linear coordinate transformation matrix. Shearing tilts the spatial axis of the image, distorting right angles into acute or obtuse angles. This simulates real-world perspective distortion, such as viewing a billboard or road sign from an oblique angle. The second family, photometric or color transformations, modifies pixel intensity values while leaving spatial coordinates untouched. Color jitter randomly perturbates the brightness, contrast, saturation, and hue of the image channels. Brightness jitter adds or subtracts scalar offsets across all RGB values, simulating changes in ambient illumination. Contrast jitter scales pixel intensities relative to their mean, expanding or compressing the dynamic range. Saturation jitter alters the intensity of color purity, forcing the network to maintain high classification accuracy even when processing monochrome or desaturated inputs. Hue jitter shifts color tones around the color wheel, preventing the model from over-indexing on specific surface colors. Gaussian noise injection adds random small floating point values drawn from a Gaussian normal distribution to each pixel. Noise injection acts as a regularizer, forcing convolutional kernels to smooth out high-frequency sensor noise and preventing weights from memorizing fine pixel artifacts. Gaussian blur applies a spatial blurring filter across the image, smoothing out sharp details. Blurring forces the network to rely on global structural shapes and macro textures rather than micro-level pixel sharpness. The third family, occlusion-based regularization, addresses a major vulnerability in deep convolutional networks: feature codependence. Deep networks often learn to rely on a single tiny, highly distinct visual feature to classify an object, such as identifying a bird exclusively by its beak. If the beak is obscured in a real-world photo, the network fails entirely. To force networks to distribute their attention across the entire object structure, engineers developed cutout and random erasing. Cutout selects a random rectangular patch within the input image, for example, a square spanning 20% of the image width, and overwrites all pixel values within that region with zeros or mean noise. When an image with a zero-filled patch is passed forward through the network, the convolutional filters covering that region receive zero activations. The network is forced to identify alternative visual cues across the remaining unobscured parts of the object. If the bird's beak is blacked out by cutout, the model must learn to recognize the bird by its wing structure, feather patterns, body shape, and tail configuration. This eliminates single-feature dependencies and significantly improves resilience against real-world physical occlusions. The fourth family, multi-image interpolation strategies, challenges traditional assumptions by combining multiple distinct images into synthetic hybrid training samples. The two most prominent techniques in this family are mix-up and cut-mix. Mix-up performs a convex linear interpolation between two entirely different training images and their corresponding label vectors. Suppose we randomly select image A, representing a dog, and image B, representing an automobile. Mix-up selects a random blending ratio, denoted as lambda, drawn from a beta probability distribution, for example, lambda equals 0.7. Mix-up constructs a synthetic input image by multiplying pixel values of image A by 0.7 and adding pixel values of image B multiplied by 0.3. Simultaneously, it constructs a synthetic target label vector, 70% dog and 30% automobile. Passing this blended, translucent image into the network forces the model to learn linear decision boundaries between classes across the entire pixel input space. Instead of forcing extreme 0 or 1 confidence predictions, mix-up regularizes the model to output smooth, calibrated confidence probabilities, dramatically reducing model overconfidence and improving adversarial robustness. Cut-mix refines this concept by combining spatial patches rather than translucent overlays. Cut-mix cuts out a random rectangular section from image B and pastes it directly into image A. The target label vector is then proportioned exactly according to the spatial surface area of the pasted patch. If the patch from image B covers 25% of the total area of image A, the target label becomes 75% image A and 25% image B. Cut-mix combines the spatial occlusion benefits of cutout with the label regularization benefits of mix-up, forcing the network to locate and classify objects within subregions of complex composite frames. While basic manual augmentations are effective, choosing the ideal combination of crop ratios, rotation angles, color jitter thresholds, and cutout sizes for a specific dataset requires laborious trial and error. To automate this process, modern computer vision pipelines utilize automated augmentation frameworks such as AutoAugment and RandAugment. AutoAugment uses reinforcement learning algorithms to search across hundreds of candidate augmentation combinations, discovering complex domain-specific policies. RandAugment simplifies this by randomly selecting a small set of transformations from a standardized pool and applying them with a single parameterized magnitude scale, providing state-of-the-art regularization with zero manual tuning. While image classification networks are designed to answer a global semantic question, what primary object dominates this image frame? Many real-world applications require far more detailed spatial awareness. In autonomous robotics, industrial quality control, and medical imaging, knowing that an object exists somewhere in an image is insufficient. The system must know precisely where the object is located, how many instances exist, and what exact spatial boundaries they occupy. This brings us to the discipline of object detection. Object detection solves two interconnected computer vision tasks simultaneously: localization and classification. Localization determines the exact spatial coordinates of an object within an image, typically framed as predicting a bounding box. A bounding box is a rectangular spatial boundary defined by four continuous numerical coordinates: the horizontal center coordinate, the vertical center coordinate, the bounding box width, and the bounding box height. Classification then assigns a categorical label and a confidence score to the visual content enclosed within that bounding box. To master object detection architectures, we must first establish three foundational mathematical concepts used across all detection frameworks: intersection over union, anchor boxes, and non-maximum suppression. Intersection over union, universally abbreviated as IOU, is the core metric used to evaluate how accurately a predicted bounding box matches the actual true bounding box of an object. Mathematically, IOU is calculated by taking the spatial area of overlap between the predicted box and the ground truth box and dividing it by the total spatial area of their combined union. OU yields a scalar value ranging from 0 to 1. An IOU of 0 indicates that the predicted box and the ground truth box do not overlap at all. An IOU of 1 indicates a perfect spatial match, where predicted boundaries align identically with ground truth. In object detection evaluation, a predicted bounding box is typically considered a correct positive detection if its IOU with a ground truth box exceeds a specified threshold, such as 0.5 or 0.75. The second concept, anchor boxes, also called default boxes or box priors, addresses the extreme variability of object shapes and sizes. Objects in natural scenes possess diverse aspect ratios and scales. A standing human pedestrian is tall and narrow, a commercial bus is long and wide, and a soccer ball is a small, uniform square. Attempting to predict arbitrary bounding box coordinates from scratch using unconstrained regression is computationally unstable. Anchor boxes resolve this by tiling a dense grid of predefined reference rectangles of varying scales and aspect ratios across every spatial cell of a feature map. For example, at each spatial grid location, the network might instantiate 9 distinct anchor boxes, 3 different spatial scales combined with 3 different aspect ratios, such as 1:1, 1:2, and 2:1. Instead of predicting raw box coordinates from scratch, the neural network learns to predict small numerical offsets, adjustments to center position, width, and height, that transform these default anchor boxes into precise object boundaries. The third concept, non-maximum suppression, abbreviated as NMS, resolves the problem of duplicate candidate predictions. Because object detection models evaluate thousands of candidate anchor boxes across overlapping spatial grids, a single physical object, such as a red automobile, will trigger high detection confidence scores across dozens of adjacent anchor boxes simultaneously. If left uncleaned, the model would output a cluttered cluster of hundreds of overlapping boxes around the single car. Non-maximum suppression is a post-processing algorithm that cleans up this candidate clutter through 3 deterministic steps. First, NMS sorts all candidate bounding box predictions across the image in descending order based on their classification confidence scores. Second, NMS selects the box with the highest confidence score, adds it to the final output list, and then calculates the IOU between that top box and all remaining candidate boxes in the frame. Third, NMS identifies any candidate box whose IOU with the top box exceeds a specified overlap threshold, such as 0.45, and completely purges it from the candidate pool. Because its spatial overlap is high, the algorithm assumes it is a redundant duplicate prediction of the exact same physical object. This process repeats iteratively until all candidate boxes have been either selected or suppressed, leaving a clean set of distinct, non-overlapping bounding box predictions. Architecturally, object detection systems are divided into two fundamental design paradigms: two-stage object detectors and one-stage object detectors. Two-stage object detectors, epitomized by the faster RCNN architecture family, split the detection process into two sequential, specialized processing pipelines. Stage 1 is candidate region proposal. A raw image passes through a deep convolutional backbone, such as ResNet, to extract a high-level feature map volume. On top of this feature map sits a specialized mini-network called the Region Proposal Network, abbreviated as RPN. The RPN slides across the feature map, evaluating anchor boxes at every spatial location. For each anchor box, the RPN outputs an objectness score, a binary probability indicating whether the box contains a foreground object versus background scene, and predicts initial coordinate offsets. The RPN selects the top candidate boxes with the highest objectness scores, passing them forward as candidate region proposals. Stage 2 is proposal classification and fine coordinate regression. Because candidate region proposals come in varying spatial heights and widths, they cannot be fed directly into dense classification layers. To standardize these proposals, faster RCNN routes the candidate feature patches through an ROI-align layer. ROI-align, short for Region of Interest Align, is a spatial feature extraction layer designed to eliminate coordinate quantization errors. In older detection architectures, cropping regions of interest involved rounding continuous spatial coordinates to the nearest discrete integer pixel index. Spatial rounding, known as quantization, caused misalignment errors that degraded localization precision for small objects. ROI-align avoids all rounding. It samples feature values at continuous floating point locations using bilinear interpolation, dividing each region proposal into a fixed grid of sampling points and extracting a uniform feature vector, such as 7 pixels by 7 pixels, without losing fractional spatial accuracy. Once ROI-align extracts uniform feature vectors for all candidate proposals, those vectors pass through dense layers that output final category classification probabilities and fine-tuned bounding box adjustments. The two-stage design of faster RCNN yields exceptional localization accuracy and high detection precision, especially for small or densely clustered objects. However, executing two sequential stages, region proposal followed by region classification, incurs significant computational overhead, making two-stage detectors relatively slow and challenging to execute in real-time edge environments. To achieve real-time detection speeds, computer vision engineers designed one-stage object detectors, represented by the YOLO framework, which stands for You Only Look Once. One-stage detectors completely eliminate the separate region proposal stage. Instead of evaluating candidate proposals in sequence, YOLO reframes object detection as a single, unified regression problem evaluated in a single forward pass through the network. In a one-stage detector, the input image is divided into an S/S spatial grid, for example, a grid of 13 by 13 cells. If an object center falls inside a specific grid cell, That cell is uniquely responsible for detecting that object. As the image passes through the convolutional backbone, each grid cell simultaneously predicts a fixed number of bounding boxes, confidence scores for those boxes, and conditional class probabilities for all target categories. Because all bounding box coordinates and classification scores across the entire image are predicted in a single parallel forward pass, one-stage detectors achieve astounding inference speeds, processing dozens or hundreds of frames per second on modern hardware, making them the standard choice for real-time video analytics, robotics, and autonomous driving. To handle objects appearing at vastly different spatial scales within a single frame, modern one-stage and two-stage detectors incorporate a feature pyramid network, abbreviated as FPN. A feature pyramid network solves a multi-scale dilemma inherent in deep convolutional backbones. In a standard backbone, early layers possess high-resolution spatial coordinates but weak semantic information. Deep layers possess rich high-level semantic abstractions but low spatial resolution due to repeated downsampling. Small objects, such as a distant pedestrian, disappear entirely from deep, low-resolution feature maps. An FPN creates a multi-scale feature hierarchy by combining a bottom-up pathway with a top-down pathway using lateral skip connections. The bottom-up pathway is the standard forward pass of the convolutional backbone, generating feature maps that shrink spatially at each stage. The top-down pathway takes the deep, semantically rich feature map from the top of the backbone and upsamples its spatial dimensions using nearest neighbor interpolation. Lateral skip connections then take high-resolution feature maps from early bottom-up layers, pass them through one-by-one bottleneck convolutions to match channel dimensions, and add them element-wise to the upsampled top-down feature maps. This creates a spatial pyramid of feature maps where every level possesses both high spatial resolution and deep semantic understanding. The detector evaluates small objects on the high-resolution lower levels of the pyramid, medium objects on middle levels, and large objects on the low-resolution upper levels, ensuring robust multi-scale detection across the entire visual frame. To achieve precise bounding box regression in object detection architectures, engineers must utilize advanced mathematical loss formulations, IOU loss, generalized IOU loss, distance IOU loss, and complete IOU loss. In early object detection frameworks, bounding box regression was optimized using standard smooth L1 loss or mean squared error applied independently to the four coordinate predictions: center X, center Y, width, and height. However, optimizing for independent coordinate errors suffers from a fundamental mathematical flaw. It treats coordinate offsets independently without considering the holistic spatial box geometry. Two bounding box predictions can have identical L1 coordinate errors, but exhibit drastically different intersection over union overlap values with the ground truth. To optimize bounding box overlap directly, researchers introduced IOU loss, defined as 1 minus the intersection over union scalar score. However, basic IOU loss suffers from a severe mathematical gradient failure. If a predicted bounding box and a ground truth box do not overlap at all, their IOU score is exactly 0. When IOU is 0, the gradient of IOU loss becomes 0, providing zero optimization signal to backpropagation to guide the predicted box toward the ground truth. To solve the zero gradient failure for non-overlapping boxes, researchers designed generalized IOU loss, universally abbreviated as GIOU loss. GIOU loss introduces a spatial penalty term based on the minimal enclosing box. Given a predicted box A and a ground truth box B, GIOU finds the smallest convex bounding box C that completely encloses both boxes simultaneously. YOLO loss calculates IOU, and then subtracts the area of the enclosing box C minus the area of the union of A and B, divided by the total area of C. If predicted box A and ground truth box B do not overlap, YOLO loss outputs a non-zero continuous scalar penalty based on how far apart the boxes sit within the enclosing box C. Backpropagation receives a clear, non-zero gradient that actively pulls the distant predicted box toward the ground truth. Distance IOU loss, known as DIOU loss, refines this concept by directly penalizing the Euclidean distance between the center points of the predicted box and the ground truth box, divided by the diagonal length of the minimal enclosing box. DIOU accelerates convergence by directly pulling box center coordinates together in continuous space. Complete IOU loss, known as CIOU loss, adds a third geometric penalty: aspect ratio consistency. CIOU loss combines IOU overlap penalty, center point distance penalty, and an explicit aspect ratio consistency penalty that measures the mathematical discrepancy in width-to-height proportions between the predicted box and the ground truth box. CIOU loss ensures that predicted bounding boxes rapidly adjust their center coordinates, spatial scale, and aspect ratio proportions simultaneously, producing state-of-the-art object detection accuracy. Beyond static images, processing video streams introduces a new dimension: temporal continuity. A video stream is a sequence of image frames captured at a constant temporal sampling rate, such as 30 or 60 frames per second. Processing each frame in complete isolation using a static object detector creates significant engineering issues. Bounding box predictions jitter, object IDs reset on every frame, and momentary physical occlusions cause objects to disappear from tracking logs. To track objects continuously across video frames, vision pipelines integrate multi-object tracking algorithms, represented by the ByteTrack and DeepSort frameworks. Multi-object tracking operates via a two-step cycle: motion prediction and data association. Step 1 is motion prediction using Kalman filters. A Kalman filter is a mathematical state estimator that tracks the position, velocity, aspect ratio, and acceleration of each bounding box across temporal frame steps. Given an object's bounding box location in frame T, the Kalman filter calculates a physics-based motion projection, predicting where the bounding box will sit in frame T+1 before the next frame is even processed. Step 2 is data association using the Hungarian algorithm and deep re-identification embeddings. When the detector processes frame T+1, it outputs a set of fresh candidate bounding boxes. The tracking pipeline matches these fresh candidate boxes against the predicted bounding boxes projected by the Kalman filter. To execute optimal matching between predicted tracks and fresh candidate detections, the system calculates a cost matrix using spatial intersection over union combined with deep feature distance. Deep feature distance is computed by passing bounding box image crops through a specialized CNN trained for person or vehicle re-identification, generating a low-dimensional feature vector for each object. The cosine distance between feature vectors measures visual appearance similarity, allowing the system to match objects even if they undergo rapid motion. The system then executes the Hungarian algorithm on the cost matrix. The Hungarian algorithm is a combinatorial optimization algorithm that computes a global minimum assignment, pairing each existing track with its optimal candidate detection in linear cubic time. If an object is temporarily occluded by a passing pole for 3 frames, the Kalman filter continues propagating its predicted position. When the object emerges from occlusion, The deep appearance feature embedding matches the candidate detection back to the original track ID, preserving identity continuity without ID switches. While object detection represents a massive leap beyond image classification, bounding boxes remain coarse approximations of spatial reality. A rectangular bounding box enclosing a diagonal object, such as a reclining human or a tilted sailboat, inevitably includes significant background clutter inside the box boundaries. For applications demanding absolute spatial precision, software systems must move beyond bounding boxes to perform segmentation. Computer vision categorizes segmentation into two major objectives: semantic segmentation and instance segmentation. Semantic segmentation assigns a categorical class label to every single individual pixel in an image. In semantic segmentation, there is no concept of individual object instances. If 5 separate people are standing next to each other in a crowd, a semantic segmentation model highlights every pixel belonging to any human in the exact same color, treating the entire crowd as a single continuous semantic blob of human pixels. Instance segmentation goes one step further. It combines semantic segmentation with instance awareness. An instance segmentation model must not only classify every pixel, but also delineate and assign a unique identity instance tag to each individual object. In the crowd example, instance segmentation highlights person 1 in red, person 2 in blue, person 3 in green, and so on, outlining exact pixel-level boundary masks for every distinct person in the frame. To execute semantic segmentation, network architectures rely on an encoder-decoder structural framework. The encoder is a traditional convolutional backbone, such as ResNet or VGG, that takes the high-resolution input image and applies consecutive convolutions and spatial downsampling layers. The encoder's job is to compress the visual input into a dense, low-resolution feature volume that captures high-level semantic context. The decoder is a symmetric spatial reconstruction network. Its job is to take the low-resolution semantic feature volume produced by the encoder and progressively upsample its spatial dimensions back to the original height and width of the input image, outputting a pixel-wise classification map where each pixel index contains a vector of class probabilities. To upsample low-resolution feature maps back to full image resolution inside the decoder, architects use two primary spatial expansion mechanisms: transposed convolutions and unpulling operations. A transposed convolution, sometimes historically called a deconvolution or fractionally strided convolution, is a learnable upsampling layer. While a standard convolution uses a kernel to collapse a spatial neighborhood into a smaller feature map, a transposed convolution reverses this spatial direction. It takes a single scalar input value from a low-resolution feature map, multiplies it by a spatial kernel of weights, and distributes the resulting weighted patch onto a higher-resolution output grid. Because the weights inside a transposed convolution kernel are learnable parameters updated via backpropagation, the network learns optimal spatial upsampling functions directly from data. However, learnable transposed convolutions suffer from a known visual artifact: checkerboard patterns. If the kernel size and stride of a transposed convolution are not carefully matched, overlapping upsampled patches create uneven weight accumulation, resulting in a high-frequency grid pattern of light and dark pixels across the output map. To avoid checkerboard artifacts, modern decoder designs often replace transposed convolutions with simple non-learnable upsampling algorithms, such as bilinear interpolation or nearest neighbor upsampling, followed by standard 3x3 convolutional layers to smooth out spatial transitions. The most iconic architecture in semantic segmentation is YOLO. YOLO established a structural framework designed specifically for high-precision segmentation on limited data volumes. YOLO gets its name from its symmetric U-shaped architecture diagram, featuring a contracting encoder path on the left and an expanding decoder path on the right. The critical innovation of YOLO is its dense horizontal skip connections linking corresponding resolution stages of the encoder directly to the decoder. In a standard encoder-decoder network without skip connections, all spatial information must bottleneck through the lowest resolution feature volume at the bottom of the network. Because spatial coordinates are severely compressed at the bottleneck, fine spatial boundaries, thin edges, and precise object contours are permanently lost, causing the decoder to output blurry, rounded segmentation boundaries. YOLO's horizontal skip connections solve this spatial bottleneck completely. At each downsampling level of the encoder, the high-resolution feature maps are copied across the network and concatenated directly along the channel dimension with the corresponding upsampled feature maps in the decoder. This structural linkage provides the decoder with access to two distinct types of information simultaneously: high-level semantic context flowing up from the deep bottleneck, and fine-grained spatial coordinates flowing horizontally from the early encoder layers. When reconstructing spatial maps, the decoder uses the semantic context to determine what class a region belongs to, and uses the uncompressed horizontal feature maps to snap exact pixel boundaries precisely around sharp edges, fine lines, and complex microscopic structures. To execute instance segmentation, the dominant architectural standard is Mask-RCNN. Mask-RCNN builds directly on top of the faster RCNN two-stage object detection framework. Faster RCNN features two output branches for each candidate region proposal: a classification branch predicting category scores, and a bounding box regression branch predicting coordinate offsets. Mask-RCNN adds a third parallel branch, a fully convolutional pixel mask branch. In Mask-RCNN, after the region proposal network selects candidate regions, and the ROI-align layer extracts uniform floating point feature maps, the candidate feature vectors are fed simultaneously into all three branches. The mask branch consists of a small fully convolutional network that predicts a binary raster mask for each candidate region, outlining the exact pixel-level silhouette of the object independently for each target class. Because ROI-align eliminates quantization rounding, the continuous floating point feature coordinates extracted by ROI-align align perfectly with the raw image pixels, allowing Mask-RCNN to output crisp, highly accurate pixel masks for complex overlapping objects. Training deep segmentation networks introduces specialized optimization challenges, particularly regarding spatial class imbalance. In many real-world segmentation datasets, such as identifying a tiny tumor on a massive brain MRI scan, 99% of the pixels in an image belong to the background class, while only 1% belong to the target object. If an engineer trains a segmentation model using standard pixel-wise cross-entropy loss, the model will quickly discover a pathological shortcut. By predicting that every single pixel is background, it achieves 99% mathematical accuracy while learning nothing about the target object. To solve severe spatial class imbalance, segmentation pipelines utilize specialized loss functions: dice loss and focal loss. Dice loss is derived directly from the Sorensen dice coefficient, a statistical metric used to measure spatial overlap between two sample sets. Mathematically, dice loss evaluates the spatial intersection between the predicted pixel probability map and the binary ground truth mask, divided by the sum of their spatial areas. Because dice loss evaluates global spatial overlap rather than averaging independent pixel predictions, background pixels contribute minimally to the loss calculation. The loss is dominated by how accurately the predicted foreground mask overlaps with the true object silhouette. If the model fails to predict the tiny tumor, dice loss outputs a massive penalty, forcing backpropagation to adjust weights until the model successfully identifies small foreground targets. Focal loss addresses class imbalance by dynamically modulating the standard cross-entropy loss based on prediction confidence. Focal loss adds a scaling factor that dynamically downweights the loss assigned to easy, well-classified background pixels while magnifying the loss assigned to hard, misclassified foreground pixels. If a background pixel is predicted with 99% confidence, its loss weight is scaled down to near zero. If a small foreground pixel is misclassified, its loss weight remains high. Focal loss ensures that optimization gradients are driven by challenging object boundaries rather than millions of trivial background pixels. Having explored mathematical foundations, core building blocks, classic paradigms, detection frameworks, and pixel-level segmentation architectures, we must examine how these systems are engineered and deployed in real-world production environments. Designing a model that achieves high accuracy on a benchmark is an important milestone. Building a production vision pipeline that executes with sub-millisecond latency on constrained hardware, handles unexpected physical edge cases, operates safely in high-stakes clinical environments, and maintains strict reliability guarantees is a completely different engineering challenge. We begin our analysis of real-world applications by examining medical image analysis, one of the most high-stakes domains in software engineering. In clinical settings, convolutional networks are deployed to analyze diverse imaging modalities, including digital radiography X-rays, computed tomography CT scans, magnetic resonance imaging MRI volumes, ultrasound signals, and high-resolution histopathology tissue slides. Medical vision systems differ fundamentally from standard consumer photograph applications in three critical dimensions: spatial dimensionality, decision consequences, and model interpretability. First, consider spatial dimensionality. While consumer photographs are two-dimensional RGB planar grids, modalities like CT scans and MRIs are three-dimensional volumetric data arrays. A CT scan consists of a sequence of two-dimensional cross-sectional image slices stacked together along an axial spatial axis, creating a continuous three-dimensional volumetric grid of voxels. A voxel is the three-dimensional equivalent of a two-dimensional pixel, representing a cubic volume of biological tissue. To process volumetric medical data natively, computer vision engineers utilize three-dimensional convolutional neural networks, abbreviated as 3D CNNs. In a 3D CNN, the sliding kernel is a three-dimensional volume defined by height, width, and depth, such as a 3x3x3 voxel filter. As the 3D kernel slides horizontally, vertically, and axially through the volumetric scan, it computes three-dimensional spatial dot products. This allows the network to detect volumetric anatomical structures, such as spherical lung nodules, complex blood vessel networks, or expanding tissue lesions, preserving continuity across all three spatial dimensions. However, 3D convolutions introduce severe computational memory bottlenecks. A single 3D feature volume consumes exponentially more GPU memory than a 2D planar map, requiring aggressive channel compression, microbatching, and memory-efficient gradient checkpointing during training. Second, consider decision consequences and clinical risk trade-offs. In standard consumer applications, misclassifying a cat as a dog carries zero physical risk. In medical diagnostics, a misclassification can alter patient outcomes. In clinical evaluation, engineers manage a strict trade-off between false negatives and false positives. A false negative occurs when the AI system fails to detect a dangerous disease, such as missing an early-stage malignant tumor, falsely declaring the patient healthy. A false positive occurs when the system flags a healthy region as diseased, triggering unnecessary surgical biopsies or patient anxiety. In diagnostic screening pipelines, software architects explicitly tune classification confidence thresholds to prioritize high sensitivity, also known as recall. Sensitivity measures the percentage of true disease cases correctly identified by the system. By lowering the activation threshold, the system ensures that nearly 100% of true pathology cases are flagged for human radiologist review, accepting a slightly higher false positive rate to guarantee that 0 malignant cases slip through unnoticed as false negatives. Third, consider model interpretability and explainability. A medical clinician will never trust or act upon a black box neural network prediction that simply outputs a numerical diagnostic score without providing physical reasoning. If an AI system claims a chest X-ray indicates pneumonia, the attending physician must see exactly which anatomical regions inform that prediction. To provide clinical transparency, computer vision pipelines integrate visual explainability algorithms, dominated by gradient-weighted class activation mapping, universally known as GradCAM. GradCAM provides visual explanations for CNN predictions without requiring architecture modifications or retraining. To understand how GradCAM works, recall that deep convolutional layers retain spatial coordinate information while capturing high-level semantic context. When an image passes forward through the network and produces a final classification score for a target diagnostic category, GradCAM calculates the mathematical loss gradients of that target score with respect to the feature map activations of the very last convolutional layer. These backpropagated gradients measure how sensitively the target score changes in response to small adjustments in each specific feature map. GradCAM averages these gradient signals across spatial dimensions to compute a scalar importance weight for each channel in the feature map. It then computes a weighted linear combination of all feature map channels and passes the result through a ReLU activation to isolate positive contributing features. The resulting output is a coarse, two-dimensional spatial heat map overlay. When visual physicians examine a GradCAM heat map, regions of the image that strongly drove the positive diagnosis are highlighted in bright warm colors like red and yellow, while non-contributing regions remain cool blue. If GradCAM highlights a distinct anatomical shadow on the lung lobe, the radiologist can confirm that the network is focusing on valid pathological evidence rather than spurious artifacts, such as an external hospital identification badge or cable wire visible on the X-ray. Our second major real-world domain is autonomous driving and robotics. An autonomous vehicle operating on public roads represents one of the most complex real-time edge computing systems ever engineered. The vehicle must process high-frequency streams of visual data, perceive surroundings, track moving pedestrians and vehicles, predict future trajectories, and execute safety-critical steering and braking decisions, all within strict execution latency budgets of less than 30 milliseconds per frame. Autonomous vehicle perception architectures rely on multi-camera perception suites combined with bird's-eye view spatial transformations. A modern self-driving vehicle mounts 6 to 8 high-resolution cameras around its chassis, covering front long-range, front wide-angle, side pillar, rear quarter, and surround views. Each camera captures a distinct two-dimensional perspective view of the world. However, an autonomous driving motion planner cannot operate in separate 2D camera pixel coordinates. It requires a single, unified 3D coordinate space centered on the vehicle, known as the bird's eye view ground plane or ego vehicle frame. To bridge the gap between 2D camera images and 3D vehicle space, modern vision pipelines utilize spatial transformer modules and cross-attention projection layers. These architecture modules take the two-dimensional feature maps extracted from all 6 surround cameras and project them mathematically onto a flat 3D spatial grid representing the road surface around the car. By transforming perspective feature maps into a continuous bird's eye view tensor, the vehicle's perception system can run object detection and tracking networks directly on the unified ground plane. A pedestrian transitioning from the view of a front-side camera to a rear-side camera is tracked as a single continuous 3D coordinate trajectory on the BEV grid, eliminating duplicate detections and frame boundary handoff glitches. Furthermore, autonomous vision systems perform monocular depth estimation. Standard camera sensors capture 2D intensity grids, discarding physical depth information, while specialized hardware like light detection and ranging, known as LiDAR, can measure physical distance by firing laser pulses. LiDAR sensors are expensive, heavy, and susceptible to severe performance degradation in heavy fog or snowstorms. Monocular depth estimation uses deep convolutional networks to predict continuous depth maps z equals f of x and y directly from standard two-dimensional RGB images. Monocular depth CNNs are trained on massive datasets using self-supervised geometric constraints. By analyzing small camera displacement between consecutive video frames, the network uses spatial motion parallax to learn physical depth models. When the trained depth network processes a single camera image, it outputs a dense depth grid where every pixel coordinate contains a predicted scalar distance value in meters, allowing the vehicle to perceive 3D obstacle distances even if secondary active sensors fail. Executing these multi-camera BEV and monocular depth networks in real-time requires strict system-on-chip edge optimization. Automobile compute platforms possess tight thermal limits and limited electric power budgets. Running unoptimized PyTorch or TensorFlow code on automotive hardware will result in dropped frames and dangerous processing delays. To achieve hard real-time latency guarantees, vision models undergo model compilation using execution engines like TensorRT or OpenVINO. Model compilation takes a trained network graph, analyzes its internal computational topology, and optimizes it specifically for the target silicon architecture through 3 key engineering operations. First, kernel fusion merges multiple sequential operations into a single compiled GPU instruction. In a standard framework, running a convolution, followed by batch normalization, followed by a ReLU activation requires 3 separate memory read-write passes between GPU global memory and local registers. Kernel fusion combines all 3 operations into a single fused mathematical kernel, executing the convolution, normalization, and activation in a single local register pass, reducing memory bandwidth consumption by over 60%. Second, tensor layout optimization reorders multidimensional array memory strides, for example, converting from channels first memory layouts to channels last layouts, matching the hardware vector vectorization registers of the target processor. Third, layer elimination identifies and purges redundant mathematical nodes, such as identity operations or static scaling parameters, streamlining execution graphs. Our third real-world domain is industrial automation and high-speed quality inspection. In modern manufacturing facilities, such as semiconductor fabrication plants, automotive stamping lines, or pharmaceutical packaging facilities, convolutional vision systems are deployed to perform automated visual quality control at blistering speeds. A typical industrial inspection camera captures and analyzes 50 to 100 items per second as products move rapidly along a high-speed conveyor belt. Industrial inspection presents a unique machine learning challenge: extreme class imbalance and unsupervised anomaly detection. In high-quality manufacturing pipelines, defective products are exceptionally rare, representing less than 0.01% of total production. Furthermore, physical defects take infinite unpredictable forms. A microscopic scratch on a silicon wafer, a hairline crack in a ceramic plate, a missing solder on a circuit board, or an improper seal on a pharmaceutical bottle. Because it is impossible to collect thousands of examples of every conceivable manufacturing flaw in advance, engineers cannot use standard supervised classification networks. To solve high-speed defect detection, industrial systems utilize unsupervised anomaly detection powered by convolutional autoencoders and feature distribution modeling. A convolutional autoencoder is an encoder-decoder architecture trained exclusively on thousands of pristine, non-defective product samples. The autoencoder learns to compress pristine product images into a bottleneck vector and reconstruct them perfectly back to raw pixel grids. Because the network has never seen a defect during training, its internal convolutional filters learn exclusively the structural patterns of normal, non-defective products. When the deployed autoencoder processes a defective product during high-speed manufacturing, it attempts to reconstruct the image using its learned normal patterns. It reconstructs the normal background perfectly, but fails completely to reconstruct the novel defect, resulting in a localized reconstruction error spike at the flaw coordinates. By subtracting the input image from the autoencoder's output image, the system generates an anomaly map. If the reconstruction error within the anomaly map exceeds a statistical control threshold, the system triggers a high-speed pneumatic actuator to eject the defective item from the conveyor belt within milliseconds. Alternatively, systems extract deep feature embeddings from pre-trained backbone layers and model the statistical distribution of normal feature vectors using Gaussian mixture models or Mahalanobis distance metrics. When a defective item passes through the system, its feature embedding falls far outside the established normal statistical cluster, flagging the anomaly instantly without requiring manual defect labels. Now that we have examined high-level applications across medicine, autonomous driving, and industrial automation, we must dive deep into the low-level practical engineering required to build, train, optimize, and scale production-grade vision pipelines. Moving a model design from a theoretical blueprint into a fast, stable, and numerically sound implementation requires mastering data pipeline optimization, advanced tensor normalization, sophisticated numerical optimizers, precision arithmetic scaling, hardware microarchitecture, and distributed multi-GPU training algorithms. We begin our technical analysis of practical implementation with the data pipeline and input bottleneck management. A common mistake made by software engineers when building computer vision systems is focusing exclusively on GPU execution speed while ignoring host data loading. Modern graphics processing units are capable of processing thousands of image tensors per second. However, if the CPU data pipeline fails to supply images to the GPU at a matching rate, the expensive GPU accelerators sit idle, waiting for input data. This condition is known as an input I/O bottleneck, where training throughput is bottlenecked not by floating point math on the GPU, but by storage read latency and CPU preprocessing overhead. To eliminate input bottlenecks, high-performance vision pipelines implement asynchronous data loading, memory pinning, and prefetching queues. Data loading pipelines read raw compressed image files, such as JPEG or PNG files, from persistent disk storage, decode the binary files into raw pixel arrays, apply randomized data augmentations on the CPU, convert arrays into floating-point tensors, and transfer those tensors across the Peripheral Component Interconnect Express Bus, known as the PCIe bus, into GPU global memory. To execute this pipeline without stalling the GPU, software systems utilize asynchronous multiprocess data loaders. In framework implementations like PyTorch, when an engineer constructs a custom dataset class by subclassing torched.utils.data, dataset, the module defines three core methods: initialization, length, and getItem. The initialization method locates image files on disk, loads target metadata, and instantiates data augmentation transform pipelines. The length method returns an integer representing the total number of samples contained in the dataset. The getItem method receives an integer index, reads the specific raw image file from disk, applies randomized geometric and color augmentations, converts the image into a floating-point tensor, normalizes pixel values to a 0 to 1 range, and returns a tuple containing the processed image tensor and its corresponding ground truth label vector. This dataset instance is then wrapped inside a multiprocess data loader. Instead of decoding and augmenting images synchronously on the main Python thread, the data loader spawns multiple parallel background worker processes on host CPU cores. Each background worker process independently reads, decodes, and augments images, placing ready-to-use tensors into a shared memory queue. Furthermore, host memory is configured with pinned memory, also known as page-locked memory. In standard operating system memory management, memory pages allocated by CPU applications are pageable, meaning the operating system can dynamically swap them between physical RAM and disk storage. When transferring pageable host memory across the PCIe bus to a GPU, the operating system must first copy the data into a temporary, unswappable driver buffer before executing the direct memory access transfer. By allocating host data buffers as pinned memory, we lock the RAM pages in place, preventing the operating system from swapping them out. Pinned host memory enables direct, hardware-level direct memory access transfers over the PCIe bus to GPU memory without intermediate CPU buffer copies, increasing host-to-device transfer bandwidth by up to 200%, combined with prefetching, where the data loader automatically prepares the next batch of input tensors in host RAM while the GPU is executing forward and backward passes on the current batch. Pinned memory guarantees that GPU compute engines operate at near 100% utilization without waiting for disk I/O. To truly optimize execution performance on hardware, system architects must understand GPU microarchitecture and the arithmetic intensity of convolutional operations. Modern graphics processing units execute computations using thousands of parallel processing cores organized into streaming multiprocessors, known as SMs. When a PyTorch or TensorFlow model executes a convolutional layer on a GPU, the work is divided into parallel threads. Groups of 32 parallel threads, known as warps, execute instructions simultaneously across vector registers. GPU memory is structured hierarchically into three primary levels: global memory, shared memory, and registers. Global memory, also called VRAM, is massive, holding gigabytes of data, but possesses high latency and restricted memory bandwidth. Shared memory is a small, ultra-fast on-chip cache shared among threads within a single streaming multiprocessor, offering memory access speeds orders of magnitude faster than global memory. Registers are tiny, ultra-fast memory units attached directly to execution logic cores. The performance of a convolutional layer on GPU hardware is governed by its arithmetic intensity, defined as the ratio of floating-point arithmetic operations, known as flops, to the bytes of memory transferred over the bus. We categorize neural network operations into two computational regimes: compute-bound operations and memory bandwidth-bound operations. Compute-bound operations are characterized by high arithmetic intensity. They execute a large number of floating-point math operations per byte of memory read from global VRAM. Standard 3x3 and 5x5 convolutions are compute-bound. Once kernel weights and feature patches are loaded into fast on-chip registers, the GPU executes dozens of element-wise multiplications and additions locally before writing results back to memory. Compute-bound operations achieve near 100% utilization of GPU compute units. Memory bandwidth-bound operations are characterized by low arithmetic intensity. They perform very few math operations per byte of memory read. One-by-one convolutions with small channel counts, element-wise activation functions like ReLU or GELU, element-wise tensor additions and skip connections, and batch normalization layers are memory bandwidth bound. The GPU spends the majority of its execution time waiting for memory pages to transfer over the global VRAM bus, while arithmetic execution units sit idle. Furthermore, on modern specialized AI accelerators, such as tensor processing units known as TPUs, and modern neural processing engines, matrix multiplication is accelerated using systolic arrays. A systolic array is a two-dimensional grid of interconnected hardware multiply-accumulate logic cells, known as max cells. In a traditional CPU or GPU, data flows between registers and arithmetic logic units for every single mathematical operation. In a systolic array, data streams continuously through a two-dimensional grid of max cells like a pulsing heartbeat. As weight values stream horizontally across the grid and activation values stream vertically down the grid, each max cell multiplies its incoming values, adds the result to an internal accumulator, and passes the raw values directly to its neighboring cells without writing back to registers or RAM. Systolic arrays execute thousands of matrix multiplications per clock cycle with minimal power consumption, driving high-throughput vision inference on server and edge hardware. Once input tensors reside in GPU memory, stable optimization relies heavily on normalization layers. To appreciate why normalization is essential inside deep convolutional networks, we must examine the mathematical phenomenon known as internal covariate shift. As visual data flows forward through dozens of stacked convolutional and activation layers, the statistical distribution of inputs entering each intermediate layer changes continuously on every training step. Because the parameters of earlier layers update during backpropagation, the mean, variance, and overall scale of feature maps in deeper layers shift unpredictably. This unstable shift forces deep layers to constantly adapt to changing input distributions, requiring extremely small learning rates and leading to slow, fragile optimization. To stabilize internal distributions and smooth the optimization landscape, computer vision architectures incorporate layer normalization techniques, dominated by batch normalization. Batch normalization, universally referred to as batch norm, normalizes the activations of intermediate feature maps across the mini-batch dimension during training. To visualize how batch normalization operates mathematically, consider an intermediate layer that receives a four-dimensional tensor volume defined by mini-batch size n, channel depth c, spatial height h, and spatial width w. Batch normalization operates independently on each individual channel C across the entire mini-batch N and spatial dimensions H and W. For a specific channel, batch norm calculates two statistical values across all images in the current mini-batch and all spatial pixel coordinates, the empirical mean scalar and the empirical variance scalar. It then subtracts the mean from every single value in that channel and divides by the square root of the variance plus a tiny epsilon constant added to prevent division by zero. Centering and scaling forces the activations for that channel across the current mini-batch to have a zero mean and unit variance. However, forcing internal activations strictly to zero mean and unit variance can constrain the representational power of the network. For instance, if an activation function like sigmoid is applied directly after zero mean normalization, the values would be restricted to the linear region near zero, stripping away nonlinear capacity. To preserve representational capacity, batch normalization introduces two learnable parameters per channel, a scale parameter gamma and a shift parameter beta. After normalizing the channel to zero mean and unit variance, batch norm multiplies the normalized values by gamma and adds beta. Crucially, gamma and beta are trainable parameters updated via backpropagation alongside the network's weights. If the optimal representation for a specific feature map requires a non-zero mean or a different variance scale, the optimization algorithm can automatically learn to set gamma and beta to restore that scale. During inference or evaluation mode, when the model processes a single image or a small validation set, computing batch statistics across the mini-batch is impossible or noisy. To resolve this, batch norm maintains running exponential moving averages of the mean and variance calculated during training. At inference time, batch norm uses these pre-computed running statistics to normalize incoming samples deterministically. Batch normalization provides three transformative engineering benefits. First, it stabilizes gradient flow, allowing networks to train with significantly higher learning rates without exploding or vanishing. Second, it reduces sensitivity to initial weight parameter initialization. Third, because the mean and variance are calculated across randomized mini-batches, batch norm introduces slight stochastic noise into intermediate activations, acting as a minor regularizer that reduces dependence on dropout. However, batch normalization suffers from a severe architectural limitation: batch size dependence. Because batch norm relies on calculating accurate mini-batch statistics, its performance degrades severely when the mini-batch size becomes very small, such as 2 or 4 images per batch. Small mini-batches produce noisy, inaccurate estimates of mean and variance, introducing high variance that disrupts model training. In high-resolution tasks like object detection, 3D medical segmentation, or instance segmentation, GPU memory limits force engineers to use microbatch sizes of 1, 2, or 4 samples per device, causing batch norm to fail completely. To operate effectively when mini-batch sizes are small or equal to 1, computer vision architects designed alternative normalization layers: layer normalization, group normalization, and instance normalization. Layer normalization computes mean and variance statistics across all channels within a single sample, completely independent of the mini-batch dimension. Layer normalization is batch size agnostic, making it ideal for architectures where batch sizes vary or are extremely small. Group normalization divides the channel dimension C into a set of predefined groups, for example, 32 groups of channels, and computes mean and variance statistics independently within each group for each individual sample. Group normalization performs exceptionally well in object detection and segmentation frameworks, maintaining stable normalization accuracy even when mini-batch sizes are reduced to a single image per GPU. Instance normalization takes group normalization to the extreme limit by computing mean and variance statistics independently for each individual channel within each single sample, evaluating statistics purely across spatial dimensions H and W. Instance normalization is widely used in style transfer and generative adversarial networks, where normalizing spatial style statistics per channel removes contrast variations while preserving structural content. With normalization layers stabilizing internal activations, parameter updates are driven by numerical optimizers and learning rate schedules. The foundation of neural network optimization is stochastic gradient descent with Nesterov accelerated momentum, commonly written as SGD with Nesterov momentum. In basic stochastic gradient descent, model weights are updated by taking a small step in the opposite direction of the gradient of the loss function. However, basic SGD struggles in parameter landscapes characterized by high curvature or noisy gradients, causing optimization steps to oscillate wildly across steep valley walls rather than accelerating down the central slope. Momentum addresses this by introducing a physical analogy, treating the optimization process as a heavy ball rolling down a hilly loss landscape. Instead of relying exclusively on the current step's gradient, momentum maintains a running velocity vector that accumulates past gradient vectors over time, scaled by a momentum coefficient such as 0.9. Nesterov accelerated momentum refines standard momentum by computing a look-ahead gradient. Rather than calculating the gradient at the current parameter position, Nesterov applies the current velocity vector first to calculate an estimated future position, and then computes the gradient at that look-ahead point. This look-ahead step acts as an adaptive brake. If the velocity is carrying the parameters toward an ascending slope, the look-ahead gradient detects the slope early and applies a dampening force, preventing overshoot and accelerating convergence toward the true loss minimum. For complex vision architectures, engineers frequently utilize adaptive optimizers, dominated by ADAM-W. ADAM, short for Adaptive Moment Estimation, maintains running estimates of both the first moment, the uncentered mean of past gradients, and the second moment, the uncentered variance of past gradients, for every individual parameter in the model. This allows ADAM to adaptively scale learning rates independently for each parameter, taking larger steps for infrequent parameters and smaller steps for frequent parameters. However, standard ADAM suffered from a critical mathematical flaw when combined with weight decay regularization. In standard SGD, L2 weight decay, which adds a penalty proportional to the square of weight magnitudes to the loss function, is mathematically identical to direct weight decay, where weight values are decayed by a small percentage on every update step. But in adaptive optimizers like ADAM, passing the L2 weight decay penalty through the adaptive moment estimate scales the decay penalty inversely with gradient variance. Parameters with large historical gradients receive smaller weight decay penalties, while parameters with tiny gradients receive massive decay penalties, causing unexpected weight distortion. ADAM-W solves this flaw by decoupling weight decay from the gradient update step. ADAM-W computes the adaptive gradient update based purely on the unregularized loss, and then applies weight decay directly to the parameters as a separate multiplicative step after the adaptive update. Decoupling weight decay restores proper regularization behavior, making ADAM-W the standard adaptive optimizer for modern vision backbones. Regardless of whether an engineer chooses SGD or ADAM-W, optimizing deep networks requires dynamic learning rate scheduling over the course of training. Setting a constant learning rate throughout training yields suboptimal performance. A high learning rate is necessary early in training to explore the parameter landscape rapidly and jump out of shallow local minima. However, as the model approaches a deep loss minimum, a high learning rate causes parameter updates to overshoot the valley floor, oscillating perpetually without settling into the optimal minimum. To manage learning rate dynamics, modern training pipelines implement learning rate warm-up combined with cosine annealing. Learning rate warm-up addresses instability during the initial steps of training. At the start of training, model weights are randomly initialized, and running statistics in normalization layers are uncalibrated. Passing data through uncalibrated networks produces massive, chaotic gradient signals. If a high initial learning rate is applied on step 1, these chaotic gradients will violently corrupt the weight initialization. Warm-up mitigates this by starting training with a tiny learning rate near 0, for example 1/10,000th, and linearly increasing the learning rate on every step over the first few epochs until it reaches the target maximum learning rate. Warm-up allows initial weights and normalization statistics to stabilize gently before aggressive optimization begins. Following warm-up, cosine annealing gradually decays the learning rate down to near 0 following a smooth cosine function curve across the remaining training epochs. The smooth, continuous decay of cosine annealing allows the optimizer to navigate complex parameter valleys, steadily refining weight precision as the model approaches convergence. Managing hyperparameter optimization across complex vision pipelines also requires systematic search strategies, Bayesian optimization, and population-based training. A vision training pipeline relies on dozens of critical hyperparameters: initial learning rate, weight decay, warm-up epoch count, cosine decay parameters, mini-batch size, dropout rates, mix-up alpha coefficients, and augmentation magnitudes. Manual trial and error hyperparameter tuning is inefficient and unscalable. To automate hyperparameter search, engineers deploy Bayesian optimization. Bayesian optimization constructs a probabilistic surrogate model, typically using Gaussian processes, that models the non-convex mapping between hyperparameter configurations and final validation accuracy. By evaluating a small set of initial hyperparameter trials, Bayesian optimization updates its Gaussian process surrogate model, calculating an acquisition function, such as expected improvement, that mathematically balances exploration of unmapped hyperparameter regions with exploitation of known hyperforming parameter zones. Bayesian optimization discovers optimal hyperparameter combinations in far fewer trials than brute force grid search or random search. For large-scale cluster deployments, software systems utilize population-based training, abbreviated as PBT. Population-based training trains a population of candidate models in parallel across a multi-GPU cluster. Periodically during training, low-performing models in the population copy the weight parameters of top-performing models, and then apply random mutations to their hyperparameters. PBT continuously optimizes model weights and hyperparameter schedules dynamically in a single training run, delivering optimized production vision models ready for deployment. As vision models and dataset resolutions expand, running training using standard 32-bit single precision floating point numbers, known as FP32, incurs severe memory footprint and hardware speed penalties. An FP32 floating point number consumes 32 bits of storage, 4 bytes per value, allocated into 1 sign bit, 8 exponent bits, and 23 mantissa bits. Storing millions of weights, activations, gradients, and optimizer states in FP32 consumes tens of gigabytes of GPU memory, limiting mini-batch sizes and choking memory bandwidth. To double training speed and cut GPU memory consumption in half, modern vision pipelines execute mixed precision training using 16-bit floating point formats, FP16 and brain floating point 16, known as BF16. An FP16 half-precision number consumes only 16 bits, 2 bytes per value, divided into 1 sign bit, 5 exponent bits, and 10 mantissa bits. Executing operations in FP16 offers 3 massive engineering advantages. First, memory consumption for activation tensors is halved, allowing engineers to double mini-batch sizes on identical hardware. Second, memory bandwidth requirements are cut by 50%, accelerating data transfer speeds between GPU global memory and computational units. Third, modern GPU architectures feature specialized hardware matrix engines known as tensor cores, which execute 16-bit matrix multiplication and accumulation operations up to 4 times faster than standard FP32 logic units. However, training natively in standard FP16 introduces a severe numerical vulnerability: gradient underflow. Because FP16 allocates only 5 exponent bits, its dynamic numerical range is restricted. The smallest positive non-zero number that can be represented in standard FP16 without underflow is approximately 6.1 times 10 to the power of -5. During backpropagation in deep networks, calculated loss gradients are frequently very small scalar numbers, such as 10 to the power of -7. In FP32, 10 to the power of -7 is represented accurately. In FP16, any number smaller than 6.1 times 10 to the power of -5 mathematically underflows directly to 0. When gradients underflow to 0, backpropagation fails, parameter updates vanish, and model training stalls out completely. To prevent gradient underflow in FP16, pipelines utilize dynamic loss scaling. Dynamic loss scaling works by multiplying the calculated loss value by a large scalar scaling factor, such as 65,536, at the start of backpropagation before gradient calculations begin. By the mathematical chain rule of calculus, multiplying the loss scalar by 65,000 shifts all backpropagated gradient values upward into the safe, representable numerical range of FP16, preventing small gradients from underflowing to 0. After backpropagation computes the scaled gradients in FP16, the pipeline unscales the gradients by dividing them by 65,000 before the optimizer updates the main master parameters. If an optimizer step encounters a numerical overflow, where scaled gradients exceed the maximum FP16 limit of 65,536, the pipeline discards that specific step, reduces the loss scaling factor by half, and continues training safely. Alternatively, modern compute hardware supports brain floating point 16, abbreviated as BF16. BF16 allocates its 16 bits differently than FP16. It uses 1 sign bit, 8 exponent bits, matching the exact exponent range of FP32, and 7 mantissa bits. Because BF16 possesses the exact same exponent dynamic range as full FP32, it is completely immune to gradient underflow, eliminating the need for dynamic loss scaling while retaining the memory savings and tensor core speedup of 16-bit execution. When training massive state-of-the-art vision models on millions of high-resolution images, a single GPU, even running mixed precision, lacks sufficient compute capacity and memory bandwidth to complete training in a reasonable time frame. Scaling training across multi-GPU clusters requires distributed scaled training. The dominant architectural paradigm for multi-GPU vision training is distributed data parallel, universally abbreviated as DDP. In distributed data parallel, The training system spawns a separate dedicated operating system process for each individual GPU accelerator across single or multi-node server clusters. The mechanics of DDP follow a synchronized process forking execution loop. First, at the start of training, the master process broadcasts an exact copy of the model's initial weight parameters to every GPU worker process, ensuring all GPUs start from identical parameter states. Second, the training dataset is partitioned across processes using a distributed sampler. On each training step, every GPU process receives a completely distinct, non-overlapping mini-batch of images. If we deploy 8 GPUs and each GPU receives a local microbatch size of 32 images, the effective global mini-batch size across the cluster is 256 images. Third, every GPU process independently executes a forward pass on its local microbatch, computing local activations and a local loss scaler. Each GPU then executes backpropagation locally, calculating gradient vectors for all model parameters based on its local microbatch. Fourth, before the optimizer can update model parameters, the gradient vectors across all 8 GPUs must be synchronized so that every GPU applies identical parameter updates. To synchronize gradients across multi-GPU processes with minimal communication latency, DDP executes an asynchronous all-reduce ring algorithm. Instead of routing all gradient vectors to a single centralized master server, which creates a massive network bandwidth bottleneck, the GPUs are organized logically into a circular communication ring. Each GPU is connected only to its left and right neighboring GPUs. During the all-reduce operation, each GPU divides its local gradient vector into equal chunks and passes a chunk to its downstream neighbor while simultaneously receiving a chunk from its upstream neighbor. In a sequence of ring pass steps, partial gradient sums are accumulated around the ring. By the time the ring cycle completes, every GPU process possesses the exact global average gradient vector for all parameters across the entire multi-GPU cluster. Furthermore, PyTorch's DDP optimizes network throughput using gradient bucketing. Instead of waiting for backpropagation to complete entirely before launching the all-reduce communication ring, DDP registers asynchronous hooks on parameter layers. As backpropagation proceeds backward from the final layer to early layers, DDP packs completed gradients into contiguous memory buffers called buckets. As soon as a bucket fills up with gradients, DDP launches the all-reduce ring transfer for that bucket asynchronously over the high-speed interconnect network while CPU and GPU engines continue computing gradients for earlier layers in parallel. Overlapping computation with network communication eliminates distributed synchronization overhead, enabling near-linear performance scaling across dozens of GPU devices. If memory footprint constraints remain severe even with 16-bit precision, such as when processing high-resolution 3D medical volumes or ultra-large vision models, engineers combine DDP with gradient accumulation. Gradient accumulation simulates massive global mini-batch sizes without increasing GPU memory usage. Instead of updating parameters after every single microbatch pass, the pipeline executes multiple consecutive forward and backward passes locally, accumulating gradients in memory without calling the optimizer. After a specified number of accumulation steps, such as 16 steps, the pipeline computes the averaged accumulated gradient, executes a single optimizer parameter update, clears the gradient buffer, and continues. Gradient accumulation allows software systems to train models with effective batch sizes of thousands of images on consumer-grade hardware. To optimize memory execution during distributed gradient accumulation in PyTorch's distributed data parallel framework, software engineers utilize the no_sync context manager. In standard distributed data parallel execution, every backward pass automatically triggers asynchronous all-reduce gradient bucket communication across processes. However, when executing gradient accumulation over multiple microbatch steps before calling the optimizer, triggering all-reduce communications on intermediate microbatch steps wastes network bandwidth. By wrapping intermediate microbatch forward and backward passes inside the DDP no_sync context manager, the system disables gradient synchronization for those intermediate steps. Gradients accumulate locally in GPU memory without triggering network communications. On the final accumulation step, the context manager is omitted, launching a single all-reduce ring communication across the cluster for the combined accumulated gradients, saving immense network bandwidth. Furthermore, software pipelines implement PyTorch's automatic mixed precision API, managed via the AutoCast context manager and the GradScaler class. When an engineer wraps model forward passes inside the AutoCast context manager, PyTorch dynamically assigns mathematical precision formats based on operation requirements. High-throughput matrix operations like 2D convolutions and linear projections are automatically cast to fast FP16 or BF16 half-precision formats, while precision-sensitive operations like softmax activations, batch normalization statistics, and cross-entropy loss functions are maintained in stable 32-bit FP32 precision. To manage loss scaling dynamically during FP16 training, the pipeline instantiates a GradScaler object. Before executing backpropagation, the scaler multiplies the loss tensor by a dynamic scaling factor. The backward pass executes with scaled gradients, preventing underflow. The scaler then unscales the gradients before the optimizer steps. If the scaler detects invalid floating point numbers or gradient overflows, it skips the optimizer step and reduces the dynamic scale factor for subsequent iterations, ensuring numerically stable half-precision training. To accelerate inference deployment without modifying underlying Python code, modern PyTorch pipelines leverage graph compilation via TorchScript and PyTorch 2.0 compilation engines. In standard eager mode PyTorch, Python overhead executes line by line, introducing interpreter latency and dynamic dispatch overhead. TorchScript resolves interpreter overhead using two compilation mechanisms: tracing and scripting. Tracing passes a dummy input tensor through the model module, recording the exact sequence of PyTorch tensor operations executed along the forward path, compiling the operations into a C++ intermediate representation graph. Scripting inspects Python code directly, compiling conditional control flow logic, loops, and dynamic branching into an optimized C++ execution graph. In PyTorch 2.0 and beyond, graph compilation is streamlined via the torch.compile API. The torch.compile engine uses TorchDynamo to capture Python execution graphs safely, passing the graph to AOT Autograd to extract backward computational graphs, and compiling the optimized graph using the Inductor compiler backend. Inductor translates high-level PyTorch computational graphs directly into fused, high-performance C++ and OpenAI Triton GPU kernels. Fused Triton kernels execute complex multi-layer sequences in a single GPU memory pass, reducing inference latency by up to 50% on production hardware. To conclude our technical analysis of computer vision, we must critically evaluate fundamental limitations, architectural vulnerabilities, paradigm shifts, and future frontiers shaping visual artificial intelligence. While convolutional neural networks have dominated computer vision for years, achieving remarkable breakthroughs across image classification, object detection, and pixel-level segmentation, they are not without deep structural limitations. Software engineers and system architects must understand where traditional convolutions fail, how generative models synthesize novel visual data, how self-supervised foundation models reframe representation learning, how modern architectural paradigms like vision transformers reframe visual processing, how pure convolutional designs have been modernized to match transformer performance, and how model compression algorithms enable deployment on constrained edge hardware. We begin our final exploration by analyzing the vulnerabilities and failure modes of convolutional neural networks. Despite their power, convolutional networks suffer from three major architectural vulnerabilities: adversarial susceptibility, texture bias, and loss of spatial part-whole relationships. The first major vulnerability is adversarial susceptibility. Deep convolutional networks, despite achieving human-level accuracy on standardized test sets, are surprisingly fragile when exposed to adversarial attacks. An adversarial attack involves adding imperceptible, mathematically engineered noise perturbations to an input image. To a human observer, an adversarial image appears completely identical to the original uncorrupted photograph, for example, a clean picture of a domestic cat. However, when passed forward through a trained convolutional network, the model classifies the image with over 99% confidence as a completely unrelated category, such as a commercial airliner or a fire engine. To understand why adversarial attacks work, we must examine algorithms like the fast gradient sign method, abbreviated as FGSM, and projected gradient descent, known as PGD. FGSM generates adversarial noise by taking the mathematical derivative of the model's loss function with respect to the input image pixels. Standard backpropagation calculates gradients of the loss with respect to model weights to update parameters during training. FGSM flips this process. It holds the model weights constant and calculates gradients of the loss with respect to raw input pixel values. FGSM then multiplies the sign of these pixel gradients by a tiny scalar magnitude epsilon, such as 0.007, and adds this noise grid directly to the input image. Because the noise is scaled by a tiny epsilon, human eyes cannot perceive the subtle pixel intensity changes. But because the noise vector aligns precisely with the direction of maximum loss ascent across millions of high-dimensional input parameters, it pushes intermediate feature map activations across the decision boundary into an incorrect classification state. Adversarial susceptibility reveals a profound truth about convolutional networks. They do not perceive physical scenes the way human brains do. They process input spaces as brittle high-dimensional mathematical manifolds, making them vulnerable to malicious exploits in security-critical applications like facial recognition access points or autonomous vehicle sign detection. To defend against adversarial exploits, pipelines utilize adversarial training. Adversarial training dynamically generates adversarial samples using FGSM or PGD during the training loop and injects them back into mini-batches alongside clean images. Forcing the network to optimize weights against adversarial perturbations smooths out steep gradient spikes in the input space, improving model robustness. The second major vulnerability is texture bias versus shape bias. Human visual perception is fundamentally driven by shape and global structural geometry. When a human identifies a clock, a chair, or an elephant, they recognize the global spatial outline and structural component relationships regardless of surface color, pattern, or texture. Convolutional neural networks, by contrast, exhibit a severe texture bias. Because early convolutional layers apply small localized kernels, such as 3x3 filters, that extract high-frequency local primitives, deep networks tend to over-index on local surface textures rather than global structural contours. This texture bias was proven empirically through landmark style swap experiments. Researchers generated synthetic hybrid images where the shape of one object, such as an elephant, was filled with the local surface texture of another object, such as the distinctive skin of an aluminum clock. When presented with these shape-texture hybrid images, standard convolutional networks consistently classified the image as a clock, relying overwhelmingly on local texture primitives while completely ignoring global elephant shape boundaries. Texture bias creates significant generalization risks when models encounter out-of-distribution domain shifts, such as recognizing objects drawn as simple line sketches, silhouetted shapes, or stylized paintings where local textures differ from natural training photographs. To mitigate texture bias and force networks to learn shape-based representations, modern data pipelines incorporate specialized stylized augmentation datasets. Stylized datasets use neural style transfer to strip natural textures from training images while preserving structural shapes, forcing convolutional kernels to learn global contour boundaries. The third major vulnerability is the loss of spatial part-whole relationships. Recall that standard convolutional networks achieve spatial translation invariance through downsampling operations like max pooling and strided convolutions. As feature maps shrink spatially, pooling layers collapse local position details, retaining information about what features exist while discarding precise coordinates of where features sit relative to one another. This creates a fundamental spatial flaw. Convolutional networks evaluate the presence of object parts without verifying their relative geometric arrangement. Consider a photograph of a human face. A standard CNN learns feature maps for eyes, a nose, a mouth, and a face outline. If a digital artist manipulates the photo, moving one eye to the forehead, placing the mouth above the nose, and scattering facial features randomly within the face perimeter, a standard CNN will evaluate the presence of all required parts and classify the scrambled image as a valid human face with high confidence. The network lacks an explicit mechanism to enforce geometric pose constraints, such as verifying that eyes must sit symmetrically above the nose and the mouth must sit below the nose. To resolve the loss of spatial pose relationships, researchers proposed alternative structural frameworks, most notably capsule networks. Capsule networks replace scalar artificial neurons with vector capsules. A vector capsule is a group of neurons whose vector direction represents the spatial pose parameters of an object part, such as position, rotation, scale, shear, and orientation, while its vector magnitude represents the probability that the part exists. Instead of discarding spatial coordinates via max pooling, capsule networks use a routing by agreement mechanism to pass vector pose outputs to higher-level capsules. A high-level object capsule, such as a face capsule, is only activated if lower-level part capsules, such as eye and nose capsules, agree on the relative spatial orientation and pose transformations of the object. While capsule networks provide elegant spatial modeling, their iterative routing algorithms incur immense computational overhead, preventing them from displacing traditional convolutional backbones in large-scale production. Beyond discriminative perception, where models classify, detect, or segment existing images, architectures power generative computer vision, allowing machines to synthesize brand new, highly realistic images from noise or text prompts. Generative computer vision architectures are categorized into three major families: variational autoencoders, generative adversarial networks, and diffusion models. The first generative family, variational autoencoders, universally abbreviated as VAEs, frames image generation as probabilistic latent space inference. A standard autoencoder maps an input image to a deterministic bottleneck vector. A variational autoencoder, by contrast, maps an input image to a continuous probability distribution defined by a mean vector mu and a log variance vector sigma. During VAE training, the encoder predicts mu and sigma for a given image. To generate a latent vector z from this distribution while maintaining an end-to-end differentiable graph for backpropagation, VAEs use the reparameterization trick. The reparameterization trick computes the latent vector z by taking the mean vector mu and adding the standard deviation vector sigma multiplied by an independent random noise vector epsilon sampled from a standard Gaussian normal distribution. Moving the random sampling step to an external noise vector epsilon allows backpropagation gradients to flow unimpeded through mu and sigma down to the encoder parameters. The VAE loss function combines two mathematical terms: reconstruction loss and Kullback-Leibler divergence loss. Reconstruction loss measures how accurately the convolutional decoder reconstructs the raw input image pixels from the latent vector z. Kullback-Leibler divergence loss, known as KL divergence, acts as a statistical regularizer. It measures the mathematical distance between the latent probability distribution predicted by the encoder and a standard unit Gaussian normal distribution. Enforcing KL divergence regularizes the latent space, making it smooth, continuous, and complete. To generate a brand new synthetic image, we simply sample a random vector z directly from a standard normal distribution and pass it forward through the convolutional decoder, outputting a fresh visual sample. The second generative family, generative adversarial networks, universally known as GANs, frames image synthesis as a two-player game theory competition between two competing neural networks, a generator and a discriminator. The generator network takes a random noise vector z and passes it through transposed convolutional layers to synthesize a fake high-resolution image. The discriminator network is a standard convolutional classification network that receives images and predicts a single binary probability score. Whether the incoming image is a real photograph from the true dataset or a fake image synthesized by the generator. Training a GAN is an adversarial min-max game. The discriminator is trained to maximize its classification accuracy, learning to spot subtle visual flaws and artifacts in generated images. Simultaneously, the generator is trained to minimize the discriminator's accuracy, updating its transposed convolutional weights to produce increasingly realistic images that fool the discriminator. To stabilize GAN training and prevent catastrophic failure modes like mode collapse, where the generator memorizes and outputs a single realistic image repeatedly, modern generative pipelines use the Wasserstein GAN with gradient penalty, known as WGNGP. WGNGP replaces binary cross-entropy loss with the Earth mover's distance, measuring the continuous statistical distance between real and generated data distributions. Furthermore, WGNGP enforces a one Lipschitz continuity constraint by adding a gradient penalty to the discriminator loss, penalizing gradient norms that deviate from 1. Lipschitz regularization stabilizes adversarial optimization, enabling high-resolution image synthesis. The third generative family, dominating modern state-of-the-art visual generation, is diffusion models. Diffusion models formulate image generation as a two-phase thermodynamic process, a forward noise addition process and a reverse denoising generation process. In the forward process, a clean dataset image is subjected to a sequence of t-discrete time steps, typically 1,000 steps. At each step, a tiny amount of Gaussian noise is added to the image according to a fixed noise schedule. By step t, the original structural content of the image is completely destroyed, leaving an unconstrained grid of pure Gaussian white noise. In the reverse process, the model learns to invert the forward process step by step, taking a noisy image at step t and predicting the exact noise component added at that step, allowing the noise to be subtracted to recover a cleaner image at step t-1. To predict noise components at each time step, diffusion models utilize a specialized 2D UNet architecture integrated with cross-attention blocks. The UNet noise predictor receives the noisy image tensor at step t alongside a scalar time-step embedding. The UNet encoder extracts spatial features across multiple resolution scales, and the decoder reconstructs a predicted noise tensor of identical height, width, and channel dimensions as the input image. To steer image synthesis using text prompts, diffusion models incorporate classifier-free guidance. During training on text-image pairs, the text prompt is converted into a sequence of text embeddings using a pre-trained language model and injected into the UNet noise predictor via cross-attention layers. During generation, classifier-free guidance computes two noise predictions simultaneously: a conditional noise prediction steered by the text embedding, and an unconditional noise prediction generated with an empty text prompt. The final noise step is computed by taking the unconditional noise prediction and extrapolating it toward the conditional noise prediction, scaled by a guidance scale parameter W. Increasing the guidance scale forces the diffusion process to adhere strictly to the semantic details specified in the text prompt, generating photorealistic imagery aligned with complex natural language descriptions. Alongside generative breakthroughs, computer vision has been revolutionized by self-supervised learning and vision language foundation models, eliminating reliance on expensive human-labeled datasets. Historically, training deep vision backbones required millions of images manually annotated by human workers. Manual labeling is expensive, slow, and prone to human error. Self-supervised learning solves data scarcity by deriving supervision labels automatically from raw, unlabeled visual data. The two dominant paradigms in self-supervised computer vision are contrastive learning and masked image modeling. Contrastive learning, represented by the SimCLR and Momentum Contrast MoCo framework families, trains vision backbones using an InfoNC loss over augmented views. Given an unlabeled image X, the pipeline applies two distinct data augmentations, such as a random crop combined with color jitter, generating two different augmented views of the exact same underlying image, referred to as a positive pair. Augmented views generated from different images in the mini-batch are designated as negative pairs. Both augmented views are passed forward through a convolutional or transformer backbone to extract normalized feature representation vectors. The InfoNC loss computes the cosine similarity between the positive pair and maximizes it relative to the sum of cosine similarities across all negative pairs in the batch. InfoNC loss forces the network to map different augmented views of the same image to nearby coordinates in feature space while pushing representations of different images far apart. By solving this contrastive matching task across millions of unlabeled images, the network learns rich, domain-agnostic visual features that transfer seamlessly to downstream classification, object detection, and segmentation tasks. Masked image modeling, represented by the masked autoencoder MAE architecture, adapts natural language masked pre-training to visual transformers. In masked autoencoder pre-training, An input image is patchified into non-overlapping patches, and a massive random mask is applied, completely removing a high percentage, typically 75% of the spatial patches. The remaining 25% of unmasked patch tokens are passed through a high-capacity vision transformer encoder. Because 75% of the image is missing, the encoder processes only a small fraction of tokens, making pre-training computationally fast. A lightweight transformer decoder then receives the encoded unmasked patch representations alongside learnable mask tokens, representing the missing 75%, and attempts to reconstruct the raw pixel values of the missing patches. To solve this reconstruction task, the network cannot rely on local pixel memorization. It must learn a deep semantic understanding of visual geometry, spatial symmetry, object structures, and natural scene textures. Once pre-training completes, the lightweight decoder is discarded, and the pre-trained encoder is fine-tuned on target downstream tasks, achieving state-of-the-art performance. Finally, Vision Language Foundation models, led by contrastive language image pre-training, universally known as CLIP, bridge the gap between visual perception and natural language semantics. CLIP trains a dual encoder architecture, an image encoder such as a CONVNext or vision transformer, and a text encoder such as a transformer language model, on hundreds of millions of image text pairs collected from the internet. During training, a mini batch of n image text pairs passes through both encoders simultaneously, generating n normalized image feature vectors and n normalized text feature vectors. CLIP computes an n by n cosine similarity matrix between all image vectors and all text vectors. The model is trained using a symmetric cross-entropy loss that maximizes cosine similarity along the true diagonal pairs while minimizing similarity for off-diagonal pairs. This joint pre-training aligns visual representations directly with natural language semantic space. An image of a dog is mapped to the exact same vector coordinate as the written text phrase, a photograph of a domestic dog. The aligned representation space of CLIP enables zero-shot classification. In zero-shot classification, a deployed model classifies images into arbitrary new categories without receiving a single training sample or gradient update for those categories. To execute zero-shot classification, an engineer converts candidate category names into text prompt strings, such as a photo of a cat, a photo of a car, or a photo of an airplane, and passes them through CLIP's text encoder to generate text feature vectors. When an unseen image is passed through the image encoder, CLIP calculates the cosine similarity between the image feature vector and all candidate text vectors. The category corresponding to the highest cosine similarity vector is selected as the prediction. Zero-shot classification allows foundation vision models to generalize instantly to novel domains, marking a new era in adaptable, general-purpose visual artificial intelligence. This brings us to one of the most transformative architectural evolutions in computer vision history, the emergence of vision transformers, universally known as VITs. For years, computer vision and natural language processing operated on entirely different architectural foundations. Natural language processing relied on transformer architectures powered by self-attention mechanisms, while computer vision relied exclusively on convolutional neural networks. The vision transformer disrupted this separation by proving that self-attention mechanisms could replace spatial convolutions entirely, achieving state-of-the-art vision performance without using a single convolutional kernel. To master vision transformers, we must unpack how a two-dimensional visual image is converted into a sequence of tokens, how spatial patchification operates, how positional encodings preserve geometry, and how the multi-head self-attention mechanism models global visual relationships. Step 1 is spatial patchification and linear projection. Standard transformer architectures are designed to process one-dimensional sequences of discrete language tokens, such as words or subword vectors. An image, however, is a continuous three-dimensional spatial array of pixels defined by height h, width w, and color channels c. To feed a two-dimensional image array into a sequence-based transformer, the vision transformer divides the image into a grid of non-overlapping square spatial patches. If an input image has a spatial resolution of 224 pixels by 224 pixels, and we select a patch size P of 16 pixels by 16 pixels, the image is physically sliced into a grid of 14 by 14 non-overlapping patches, yielding a total of 196 patches. Each individual 16 by 16 color patch contains 16 multiplied by 16 multiplied by 3 channels, which equals 768 raw numerical values. The vision transformer flattens each 16 by 16 patch into a one-dimensional vector of 768 numbers, and passes it through a trainable linear projection matrix. The linear projection maps each 768-element patch vector into a d-dimensional embedding vector, such as a vector of 768 floating point numbers. The result of patchification and linear projection is a sequence of 196 spatial patch tokens, functionally equivalent to a sentence of 196 words entering a text transformer. Additionally, following language transformer conventions, a trainable class token is prep-ended to the start of the patch sequence. This class token acts as a global summary node that aggregates information across all spatial patch tokens throughout the transformer layers. Step 2 is positional encoding. Because the self-attention mechanism evaluates all input tokens simultaneously in parallel, self-attention is inherently permutation invariant. If you shuffle the sequence of 196 patch tokens randomly, standard self-attention produces the exact same output, completely unaware of spatial ordering. To inform the model of spatial geometry, trainable 1D or 2D positional embeddings are added element-wise to each patch token vector before entering the transformer encoder. These positional vectors encode spatial grid coordinates, allowing the model to know which patch corresponds to the top left corner, center, or bottom right edge of the image frame. Step 3 is multi-head self-attention. Once patch tokens and positional embeddings are summed, the token sequence enters stacked transformer encoder blocks, where spatial relationships are computed via self-attention. In a self-attention layer, every input token vector generates 3 distinct learned vectors through matrix multiplications: a query vector Q, a key vector K, and a value vector V. To calculate self-attention, the query vector of a specific patch token is multiplied by the key vectors of every single other patch token in the image using a dot product operation. The resulting scalar dot products represent raw attention interaction scores, measuring how strongly that patch should attend to or interact with every other patch across the frame. These attention scores are scaled by the square root of the key vector dimension to prevent numerical instability, and pass through a softmax activation function to output a normalized probability distribution of attention weights that sum to 1. Finally, the attention weights are multiplied by the value vectors of all patch tokens and summed together, producing an updated contextual embedding vector for each patch. By running multi-head self-attention, where multiple parallel sets of query, key, and value projection matrices operate simultaneously, the network allows each spatial patch to learn diverse interactions across different representation subspaces. One attention head might focus on local visual boundary transitions, while a parallel attention head focuses on long-range semantic relationships linking distant objects across the entire frame. Comparing vision transformers to convolutional neural networks reveals a fundamental architectural trade-off: spatial inductive bias versus global expressive capacity. Convolutional neural networks possess strong hard-coded spatial inductive biases, locality and translation equivariance. By design, a convolutional filter evaluates only small localized pixel neighborhoods, such as 3x3 grids. It assumes mathematically that neighboring pixels are strongly related, while distant pixels are independent. Furthermore, weight sharing enforces translation equivariance across spatial coordinates. These built-in inductive biases act as structural guardrails, allowing CNNs to generalize exceptionally well when trained on small or medium-sized datasets. Vision transformers, by contrast, possess virtually zero spatial inductive biases. In a vision transformer, self-attention evaluates dot products between all pairs of patches across the entire image simultaneously, starting from the very first layer. A patch in the extreme top left corner can interact directly with a patch in the extreme bottom right corner in layer 1 with zero spatial constraints. The model is forced to learn the basic laws of 2D spatial geometry and local proximity from scratch purely from data. Because VITs lack spatial inductive biases, training a vision transformer on a small dataset yields poor performance. Without structural guardrails, the model overfits or fails to learn spatial representations. However, when vision transformers are trained on massive datasets containing tens or hundreds of millions of images, such as ImageNet 22K or private web-scale vision corpora, their lack of restrictive inductive biases becomes a massive advantage. Unconstrained by localized 3x3 sliding windows, VITs scale their representational capacity continuously with data and compute, outperforming traditional CNNs on massive high-capacity visual tasks. Furthermore, self-attention incurs a specific computational complexity cost: quadratic spatial complexity. Mathematically, calculating dot products between all pairs of n-patch tokens requires n-squared operations. If an image resolution is doubled, the number of patches quadruples, causing the self-attention memory and flop requirement to increase by a factor of 16. This quadratic spatial complexity makes naive vision transformers computationally expensive for dense, high-resolution tasks like object detection and pixel-level segmentation. To solve quadratic spatial complexity in dense visual tasks, modern architectures rely on hierarchical vision transformers, epitomized by the Swin transformer. The Swin transformer solves quadratic spatial complexity by introducing shifted windows and hierarchical feature maps. Instead of computing global self-attention across the entire image, the Swin transformer partitions the patch grid into local, non-overlapping spatial windows, such as windows containing 7x7 patches. Self-attention is computed exclusively within each local window, reducing computational complexity from quadratic to linear relative to image size. To allow information to flow between different local windows, the Swin transformer alternates between standard window attention and shifted window attention across consecutive layers. In shifted window attention, the spatial boundaries of the local windows are shifted by half the window size, for example, shifting by 2 patches. Shifted windowing creates cross-window connections, allowing neighboring windows to exchange information without increasing computational complexity. Furthermore, the Swin transformer builds a hierarchical feature representation by inserting patch merging layers between transformer stages. Patch merging concatenates neighboring 2x2 groups of patch tokens and applies a linear projection layer, having the spatial resolution while doubling the channel depth. This produces a spatial pyramid of feature maps similar to traditional convolutional backbones like ResNet, allowing SWIN transformers to be plugged directly into state-of-the-art feature pyramid networks for object detection and instance segmentation. The success of vision transformers led computer vision researchers to ask a profound architectural question. Was the superior performance of transformers driven by the self-attention mechanism itself, or by the modernized architectural choices and training techniques introduced alongside VITs? To answer this question, researchers developed modern hybrid architectures, led by the CONVNeXT family. CONVNeXT reevaluated standard pure convolutional networks, specifically ResNet backbones, and systematically modernized their structural design by applying key architectural principles borrowed directly from vision transformers, creating a pure convolutional network that matches or exceeds transformer performance while retaining CNN efficiency. The modernization of ResNet into CONVNeXT follows 5 crucial structural transformations. First, adjusting stage compute ratios. Standard ResNet 50 allocated block counts across its 4 feature stages in a ratio of 3, 4, 6, 3. CONVNeXT adjusted this ratio to 3, 3, 9, 3, matching the compute allocation of SWIN transformers and devoting significantly more depth to high-level feature extraction stages. Second, modernizing stem design. Standard ResNet used a heavy 7x7 convolution with a stride of 2 followed by max pooling as its input stem, aggressively downsampling images. CONVNeXT replaced this with a non-overlapping 4x4 patchifying convolutional layer with a stride of 4, matching the exact spatial patch projection mechanism of vision transformers. Third, adopting large depthwise convolutions. Standard ResNet used small 3x3 convolutions. CONVNeXT transitioned to large 7x7 depthwise separable convolutions. A 7x7 depthwise convolution expands the spatial receptive field of each layer significantly, allowing pure convolutional networks to capture broad spatial context similar to local self-attention windows without incurring quadratic n-squared computational complexity. Fourth, utilizing inverted bottleneck blocks. Standard bottleneck residual blocks compress channel dimensions in the middle layer. CONVNeXT adopted inverted bottleneck blocks, similar to transformer MLP blocks, where hidden channel dimensions are expanded by a factor of 4 in the middle depthwise layer before being compressed back at the output, preserving rich high-dimensional feature representations during spatial filtering. Fifth, streamlining layer normalization and activations. Standard ResNet placed batch normalization and ReLU activations after every single convolutional layer. CONVNeXT replaced batch normalization with layer normalization and replaced ReLU with Gaussian error linear units, known as GELU. Furthermore, CONVNeXT drastically reduced the frequency of normalization and activation layers, placing only a single layer norm and a single GELU activation within each inverted block, smoothing gradient dynamics and accelerating execution speed. CONVNeXT proved that pure convolutional neural networks, when modernized with large depthwise filters, inverted bottleneck structures, and streamlined normalization, achieve state-of-the-art accuracy, outperforming vision transformers on image classification, object detection, and segmentation while executing faster and consuming less memory. Whether a software engineering team deploys advanced CONVNeXT backbones or vision transformers, deploying these high-capacity models to low-power edge hardware, such as smartphone microprocessors, wearable medical devices, automotive microcontrollers, or embedded IoT cameras demands specialized model compression and quantization. High-capacity vision models often contain tens or hundreds of millions of parameters, demanding hundreds of megabytes of memory and billions of floating-point operations per frame. Running uncompressed models on edge devices leads to severe memory exhaustion, high latency, and rapid thermal throttling. To compress model footprint and accelerate edge execution, software engineers rely on three primary optimization techniques: quantization, knowledge distillation, and pruning. The first technique, quantization, converts model parameters and activation tensors from high-precision floating-point formats to low-precision integer formats, dominated by 8-bit integers, known as INT8. An INT8 integer consumes only 8 bits of storage, 1 byte per value, representing whole numbers ranging from -128 to +127. Converting a model from 32-bit FP32 to 8-bit INT8 reduces model file size and memory footprint by exactly 75%. A model that originally required 400 megabytes of memory in FP32 consumes just 100 megabytes in INT8. Furthermore, executing math in INT8 accelerates computational execution. Modern microprocessors and specialized neural processing units, known as NPUs, feature dedicated integer vector units that execute INT8 arithmetic up to 4 times faster than floating-point math while consuming a fraction of the electrical energy. To quantize a model accurately, software pipelines implement two distinct workflows: post-training quantization and quantization-aware training. Post-training quantization, abbreviated as PTQ, quantizes a fully trained FP32 model after training is complete, without requiring model retraining. PTQ works by passing a small representative calibration dataset, such as 100 sample images, forward through the trained FP32 model. The calibration pipeline records the minimum and maximum floating point activation values across all layers and calculates scalar scaling factors and integer zero-point offsets that map continuous floating point ranges to discrete INT8 integer ranges. While PTQ is fast and requires zero retraining, converting high-precision weights directly to INT8 can introduce quantization noise, causing accuracy degradation in highly sensitive architectures. To prevent quantization accuracy loss, engineers execute quantization-aware training, universally known as QAT. Quantization-aware training models quantization error directly during backpropagation training. During the forward pass of QAT, fake quantization nodes clamp continuous FP32 weights and activations to simulated INT8 discrete levels, allowing the network to experience precision loss during training. During the backward pass, backpropagation computes gradients using straight-through estimators, adjusting master FP32 weights so that they become inherently resilient to integer rounding. When QAT training completes, converting the model to true INT8 yields near-zero accuracy loss compared to the full precision baseline. The second model compression technique is knowledge distillation. Knowledge distillation uses a teacher-student framework to transfer the learned representational capacity of a massive, highly complex model, or an ensemble of multiple models, into a small, lightweight student network designed for edge deployment. The teacher model is a high-capacity architecture, such as a deep vision transformer or a massive CONVNeXT ensemble, that has been trained to achieve peak accuracy on a massive dataset. The student model is a lightweight, parameter-efficient network, such as a small mobile net, with a fraction of the teacher's layers and channels. Instead of training the small student model exclusively on hard binary labels, Knowledge distillation trains the student to match the softmax output probability distribution generated by the teacher model. To extract rich dark knowledge from the teacher, knowledge distillation applies temperature scaling to the softmax function. Standard softmax computes class probabilities by exponentiating raw logit outputs. When a model is highly confident, standard softmax outputs a probability of 0.99 for the top class and near zero probabilities, such as 10 to the power of -6, for all remaining classes, hiding subtle relationship information. Temperature scaling divides raw logit outputs by a scalar temperature parameter T, such as T equals 4, before computing softmax. Raising the temperature T softens the probability distribution, revealing subtle dark knowledge predictions. For example, when processing a picture of a dog, a high-temperature teacher model might output a probability of 0.7 for dog, 0.2 for cat, 0.08 for horse, and 0.001 for car. These softened dark knowledge probabilities encode rich structural relationships learned by the teacher, telling the student that a dog looks visually similar to a cat, somewhat related to a horse, and completely unrelated to a car. Training the lightweight student network to match these softened teacher distributions using Kullback-Leibler divergence loss allows the small student model to achieve accuracy far exceeding what it could learn from hard one-hot labels alone. The third model compression technique is structured pruning. Pruning analyzes parameter importance across a trained network and permanently removes redundant weights, filters, or entire channels that contribute minimally to final outputs. In unstructured pruning, individual weight matrix elements whose absolute values fall below a small magnitude threshold are set to 0. While unstructured pruning creates sparse matrices that reduce parameter counts, standard hardware processors cannot execute sparse matrix math efficiently, yielding minimal real-world latency speedup. In structured pruning, entire convolutional filters, attention heads, or channel dimensions are removed completely. If a convolutional layer contains 64 filters, structured pruning might identify 16 filters with low activation magnitudes, purge them entirely, and shrink the layer to 48 filters. Structured pruning physically reduces tensor dimensions, allowing standard hardware engines to execute smaller, dense matrix operations faster without requiring specialized sparse execution hardware. As computer vision continues to converge with multimodal artificial intelligence, software engineers must master the integration of visual backbones with large language models and novel 3D neural scene representations, large multimodal models, neural radiance fields, and three-dimensional Gaussian splatting. The emergence of large multimodal models, abbreviated as LMMs, represents a major synthesis of computer vision and natural language processing. An LMM enables a system to receive both high-resolution visual images and natural language text prompts, reasoning jointly across visual and textual contexts to answer complex questions, generate visual code, solve multi-step spatial logic puzzles, or describe fine-grained visual details. Architecturally, large multimodal models combine three primary components: a pre-trained vision backbone, a cross-modal projection connector, and a large language model backbone. The pre-trained vision backbone, typically a high-capacity vision transformer or CONVNeXT pre-trained with clip contrastive alignment, processes the incoming visual image, outputting a sequence of spatial visual token vectors. However, visual token vectors output by a vision backbone sit in a different mathematical vector space than the token embeddings expected by a large language model. To bridge these vector spaces, LMM architectures utilize a cross-modal projection connector. The projection connector can be a simple linear projection matrix, a multilayer perceptron, or a specialized perceiver resampler block. The connector maps the d-dimensional visual token vectors into the exact embedding dimension of the language model. These projected visual tokens are then prepended directly to the sequence of text prompt tokens entering the large language model. The large language model treats the projected visual tokens as if they were special word embeddings, executing multi-head self-attention across both visual and text tokens simultaneously. During autoregressive text generation, the language model predicts output word tokens conditioned on the visual token representations, enabling visual question answering, spatial reasoning, and visual instruction following. In the emerging field of embodied artificial intelligence and robotics, vision models are integrated directly with physical motor control through vision language action models, known as VLA models. A vision language action model bridges high-level visual perception with low-level robotic manipulation. In a VLA model, such as RT1 or RT2, the system receives multi-camera video streams of a physical environment alongside a natural language command, such as pick up the red mug and place it on the top shelf. The visual backbone extracts spatial feature embeddings, which are combined with text embeddings and passed into a transformer backbone. Crucially, instead of outputting categorical classification labels or bounding box coordinates, the VLA model outputs discretized action tokens. An action token represents a discretized numerical motor command for a robotic arm, 3D spatial end effector translation deltas along X, Y, and Z axes, 3D rotation deltas for roll, pitch, and yaw, and a binary gripper state token controlling opening or closing of the robotic hand. By training VLA models on thousands of physical robotic execution trajectories, the neural network learns to translate raw camera pixels and text instructions directly into continuous closed-loop motor control, enabling autonomous robots to interact with real-world physical objects. Beyond two-dimensional images and static bounding boxes, computer vision has expanded into 3D neural scene synthesis, dominated by neural radiance fields and three-dimensional Gaussian splatting. Neural radiance fields, universally known as NeRFs, represent continuous 3D physical scenes not as explicit polygonal meshes or discrete voxel grids, but as implicit continuous functions parameterized by deep, fully connected neural networks. A NeRF takes a continuous 5D spatial coordinate vector as input, 3D spatial position x, y, z, and 2D viewing direction angles theta and phi. The NeRF network passes these 5D coordinates through dense layers, outputting two physical predictions: an RGB color vector and a volume density scalar representing opacity. To capture high-frequency spatial details, such as sharp edges, specular reflections, and fine surface textures, NeRF applies positional encoding to the input 5D coordinates using high-frequency sine and cosine functions before feeding them into the network. To synthesize a novel camera view of a 3D scene, NeRF executes volume rendering along camera rays. For each pixel in the target camera frame, a virtual ray is cast from the camera origin through the pixel coordinate into the 3D scene. The network samples points along the ray, evaluates RGB color and volume density at each point, and integrates these values using numerical quadrature. Volume rendering computes how light accumulates and attenuates along the ray, outputting a photorealistic synthetic pixel color. By optimizing NeRF parameters across a collection of two-dimensional photographs taken from different viewing angles using mean-squared error loss between rendered rays and true image pixels, the network learns a complete, photorealistic 3D representation of complex physical scenes. To accelerate 3D scene synthesis to real-time speeds, computer vision architects developed three-dimensional Gaussian splatting. While NeRF relies on evaluating deep neural networks millions of times per ray, resulting in high rendering latency, 3D Gaussian splatting represents physical scenes using millions of explicit, learnable 3D Gaussian primitives. Each 3D Gaussian primitive is defined by 5 physical parameters: a 3D center position vector, a 3D covariance matrix controlling spatial shape and scale, an opacity scalar, a color vector, and spherical harmonics coefficients that model view-dependent lighting reflections. Rendering a 3D scene represented by Gaussian splats is executed via tile-based rasterization. The 3D Gaussians are projected onto the 2D camera image plane, sorted by depth from front to back, and rasterized in parallel across GPU screen tiles using hardware-accelerated alpha blending. 3D Gaussian splatting achieves photorealistic 3D scene rendering at over 100 frames per second at high resolutions, enabling real-time spatial computing, robotic simulation, and virtual reality rendering. As we look toward the future horizon of artificial intelligence, computer vision is expanding into neuromorphic event-based processing, optical neural networks, and quantum vision algorithms. Neuromorphic event-based processing departs from traditional frame-based cameras. Standard cameras capture full spatial pixel grids at fixed frame rates, such as 30 frames per second, generating massive redundant data when scenes remain static. Neuromorphic event sensors, by contrast, operate asynchronously. Each pixel on an event sensor operates independently, firing a digital spike event only when it detects a local change in logarithmic light intensity above a threshold. Neuromorphic vision algorithms process these asynchronous event streams using spiking neural networks, abbreviated as SNNs. In a spiking neural network, artificial neurons communicate via discrete temporal spikes, integrating charge over time. Spiking vision processors execute visual perception with ultra-low latency and microwatt power consumption, making them ideal for high-speed robotics, spatial tracking, and space-constrained edge applications. Simultaneously, researchers are developing photonic and optical neural networks. Traditional electronics rely on electron movement through silicon transistors, incurring capacitive heat losses and clock speed limits.